I don't know what the flicker is. There we go.
We're going. We are live. Hello, everybody. Thank you. Today's date is September 29th, 2019, and I'm here with Bob Greenyer of the Flieschmann Memorial Project. I'm pretty excited about this. It's one of my first, I would say, big guests, but let's get right into it, shall we? So if you guys have any questions, feel free to chat. It's going to show up live on the screen, so we can record it for later. And yeah, let's get into it. So, welcome. Appreciate you being here. Are we good? You can hear me? All right, all right. So, I guess tell everybody a little bit about yourself first, just for people who don't know who you are.
My father was a farmer. I grew up in Worthing, which just happens to be the town that Martin Fleischmann's family fled to prior to the Second World War to go and live. And I have a fairly large family, and yeah, so it's a small. Well, it's the largest town in West Sussex, but it's not a big town by international standards. And I had the fortune of a father that would let us, use explosives and drive around in old bangers on our farm or weld things together or make rockets or all kinds of different things that we were just boys being boys. But it was science, it was exploration and so forth. So I had that fortune in my early childhood to have access to machine shops and so forth, and I got a fascination with science. One of the first things I did was I converted my bedroom to run off solar, so I created this whole sort of parabolic mirror array that went onto a solar panel, and the solar panels were really expensive then, so I had to come up with some sort of solar concentration system. And then I stored that in some batteries. There weren't any fancy lithium ones back then, but then I used that for my lighting in the evening and for my fan during the summer. And I built a solar system for heating the swimming pool that we had later in my childhood. It's a sort of motel that we switched from farming to motel. Long story.
A real estate investment type of deal? I mean, there's...
No. What it was is there were subsidies that came in to Dutch farmers in the 1970s, and within 2 years, those subsidies destroyed my father's two prime businesses. He used to grow like something 16 tons of tomatoes a week, and he grew mushrooms before that, and we also grew potatoes and flowers. But the two core products, the tomatoes and the croissants, it was cheaper for them to deliver with the subsidies in refrigerated lorries anywhere in the UK than my father's cost of production. So
right.
This is where another nation providing subsidies to their producers can destroy in an incredibly small amount of time a multi-generational business. And then once you're destroyed, they can remove the subsidies, and they've got the market. So
disruptive, disruptive, arbitrage, in a way.
Yeah. But of course, I learned about the greenhouse effect. My father actually used the real greenhouse effect. Let's put it that way. My father used to use these paraffin burners to increase the temperature of the greenhouses to lengthen their growing season, but also it produced carbon dioxide, so you got a double whammy. And carbon dioxide is a food. It's good for plants. They like it. It's not a poison. And so although we did use one image I have as a child is every year to remove all the parasites and stuff that were growing that may have accumulated in the soil. at the end of the season. What you would actually do is you would take a pile of sulfur and you would put it in the middle of the greenhouse. These greenhouses were massive. And you would actually light the sulfur, it would make sulfur dioxide, and you were effectively fumigating the entire greenhouse. And then I imagine, I wasn't there, but you would probably vent this to the environment. That would kill all the parasites in the environment. So yeah, I learned about closed systems, about chemical use in closed systems in order to improve the growing potential and the pest resistance of different things. And the other thing is I learned about the importance of pollination. So for instance, we used to actually manually go around with Q-tips, like cotton earbuds, and pollinate the tomato plants. You know, I started work at the age of 4. Some people might find that's odd, but you know,
it's child labor. There's some child labor laws, I'm sure that.
When I say started work, for me it was fun. I was learning stuff. You know, my father wasn't whipping me. I wasn't on a ball and chain.
That's good.
And in a small wood box. No.
That's the point of having kids, right? I mean, that's why I had kids. To be honest, is a little extra labor, help around the house.
You've got them running the generator right now to run your laptop. Right?
Yeah, exactly. Actually, I have one of them holding a microphone boom.
Yeah. That was me growing up on a farm, and my parents, for various reasons, found the local education wasn't up to scratch, and there was a scheme that was available. I got to a very good school through that scheme, and then I got to a good university, an engineering university, and did a course called Special Engineering Program, which some people called someone else's problem, but or systematic eradication of personality. It was like every course they at Brunel University, and you had to do every course. So it was like material science, electrical, electronics, psychology, accounting. You did everything everyone else was doing.
So you have a broad spectrum.
Yeah. So that I continued on in the second year on the sister course, which was a manufacturing engineering specific course, and that was more practical based, and essentially. I had the opportunity to work in the pharmaceutical industry, and then the advertising and promotional businesses at the top level, promoting some brands, and that I eventually walked away from. There was a moment where this organization that I was supporting were promoting tobacco products by handing out tobacco products to children on the beaches of Africa, and that for me was the moment where I said,
that sucks.
Industry.
The magazines, or like what particular format did they use?
You could find out if they wanted to, but it was right at the top level of international marketing. Then I happened to work right in the center of the city, in the belly of the beast. And ultimately, it was a situation where I found myself left justifying text boxes in PowerPoint presentations because someone else was brought in to help me, but they didn't really know how to use the software, and they were adding to the time it was taking me to do the work. And when I was invited to the Royal Society to talk about the Martin Flieschmann Memorial Project, and I thought, this is it. I don't even agree with the way banks make money. I know they provide a mechanism by which money flows in the system, and it's the mechanism we have to work with, or seem to have to work with. But I made them look good for 1.5 years, and at that point I thought, I'm not learning anything here. I really want to be
stagnating. And you got to do what makes you happy too, right? I mean, did it make you happy? You got to do what makes you happy.
No.
Yeah, exactly. That's exactly. I think that's the most important thing, is you do what makes you happy. So like you just talked about the banks too. This totally. I wasn't even going to ask this question, but it ties in. What is your opinion on cryptocurrency? How do you think that will affect, maybe the engineering and applied science community, or just in general? What do you think about cryptocurrency?
There's always the question about where the crypto currencies, came from. I mean, from the point of view of monetary system, they are divisible. They can hold their value, although they go up and down. It's gonna crash.
Right. Well, that's like any market, though. I mean, that's pretty much any market.
Yeah, but I mean, if there genuinely is a limit to the amount you can mine, where, for
Right.
instance, Bitcoin supposedly is that, then and it is divisible to any amount, then it has that kind of gold-like money property that gold has that fiat actually technically doesn't.
It
And
doesn't. Yeah.
so, fiat's always failed at some point. I mean, the dollar's done very well, but what has had to be done to maintain that longevity of a currency?
Well, right. I mean, I think it's lost over its time of its inception. It's lost like 97% of its worth technically, and most of that happened in 1971 when Nixon. Yeah, exactly. So yeah, cool. I just want to get your take on that.
Well, essentially, I think
it depends on the blockchain too, right? Because I mean, obviously, there's some blockchains that are very much incorporated with the banks and stuff like that. I don't know how much you know about it.
There is the thing is like, was a cryptocurrency invented for the purpose of inoculating the population to the idea of it, getting them used to it, and then when they're all used to it, said you can trade it in for this other cryptocurrency, which by the way you're going to be paying your taxes in, and therefore you have to use it, and everyone has to use it, and then everyone can monitor every transaction that's ever done by anyone.
Right. Yeah, that's. I mean, the original Bitcoin, the gold standard, right? I think was meant to be decentralized and all that kind of stuff. But now, as you say, there's people who want to get their hands, and they didn't realize that it would be the way it is what it seems like. So yeah, I completely agree with you. I know what you're saying.
The real fear is that players, like I can see even on the channel that we're using now to broadcast this, you can now pay people on Skype directly through Skype.
Yeah.
Okay, and that's one step away from them having a cryptocurrency to facilitate that transfer, so they're not going through the same monetary channels. You've got Facebook considering something which is kind of sounds like a cryptocurrency, but actually it's not in the same vein.
It's centralized. Yeah.
So and with their footprint, it's really very scary. And it should be scary even for countries.
Yeah. Countries in general. Yeah, I mean, countries in general, I think most governments especially are scared a little bit of the potential and which way it goes. We're kind of at a crossroads, right? It seems like. So I don't know how much you know, like there's actually governance systems too built into some of the blockchains, which I think is, that's very, very interesting. All right, well, let's move on because we're not here to talk about cryptocurrency too much, right? I just want to get your take on it. We moved into it. It felt right. So, how did you first get your start in LENR and cold fusion and all that kind of stuff?
Well, I have to say that the start was, if I carry forward from my early years of being interested in alternative energy, and from a farming point of view, that the concept of greenhouse gases connected with me way back when. I was an ardent reader of New Scientist, and I'm old enough, being 40, I think I'm 47 now, kind of not lose track after a while. But basically, the original Pons and Flieschmann announcement, I remember, I was all over it. It was right up my street, and then I saw the kind of takedown, as it were, and I thought, this doesn't make any sense to me. Why would these people who are so intelligent and have, particularly in the case of Flieschmann, they had a real name for themselves in the world of electrochemistry and Raman spectroscopy and different aspects of his expertise. He was really at the top level. Why would they put themselves at this risk? And that always left me with a bad taste in my mouth. And I have to be honest that when these things started to get a little bit more exposure in 2011 with the advent of the claims made by one Italian Andrea Rossi.
Yeah.
I started paying attention to the current status in the field.
Right.
I mean, I've been to the Peak Oil Conference in 2006 because, I was that concerned. I self-funded myself to go there and listen to that. And that, for me, when I came away from that conference and they were saying that, look, even if they ever get a fusion, hot fusion to work, they're never going to be able to produce enough fuel. And they have enough fuel to run a 1 megawatt test reactor for a year, but it's going to take a very long time to get that fuel together. And the conference was, I mean,
and do you think, sorry to interrupt, but do you think that that's because of like the condensed matter physics angle of things? Like, do you think it's on that side, or you know what I mean? Like, what do you think is the problem with that approach, with the hot fusion approach?
Well, yeah, I mean, you've hit the nail on the head. Is that what there's in my view and my level of understanding, there is one central, and I'm going to call it a lie. They say we are trying to create on Earth what goes on in the sun, right?
Right.
But we're not. Firstly, the sun is something like 98.8% of the mass of the
right.
solar
It has
system.
a far greater order of magnitude as far as energetic density. Yeah.
Yeah, and the gravity is there.
Right.
So we simply cannot create those things. So they're compensating by increasing the temperatures, which means everything wants to be apart from everything, which means that you have to work harder and harder to get
put it together.
To collide.
Yeah.
And then you're always working in a situation where you're looking for one particle to interact with one particle on a probability basis, where
right.
You know, that's even if you've got the deuterium or deuterium and tritium available.
Right.
You know, that's once you have those things available, and then they're producing fast neutrons, and the fast neutrons are coming out. This is a separate argument. It actually does produce fast neutrons, and that makes everything really difficult to contain.
Right.
But the central point is that it isn't condensed matter. It's kind of like a plasma.
It's a plasma, right? Which is excited gas essentially, and very far apart. Molecular structure. I mean, very, very far apart atoms.
Not molecular. It's barely atomic.
Yeah.
I mean, you are basically getting atomic deuterons and tritons and trying to get them to hit each other by having such kinetic.
Atomic and even subatomic, really. I mean, it's all subatomic like probabilities, and it's like a forceful lottery. I get right. It'd be like it's like a forceful lottery. We're just.
I just. You know, it's wonderful engineering. It keeps a lot of people employed, but I think that's the point.
I think that's that's a main issue, right? Yeah, and that's a main issue I think that we're having, and you know, this is a bigger, more broad scale, like holistic look at things, I guess. But the social science really is what is holding us back a lot. If it's always up to funding, then are we really progressing forward? You know, it's kind of like, and it almost becomes like it's like religious dogma, and the religion is money.
There is money for outcomes to occur. You know, in the US, for instance, people can easily spend 100 million on a candidate that fails in a political campaign. But trying to get the very same people to open their pocketbooks for a few $1,000s to do something that literally will fundamentally change the course of humanity, it's like, why? Well, you have to ask, why are they willing to give so much to a political campaign, and they're not? What do they think they're getting in return for that, which they're not going to get in return, or their children's not going to get in return from genuinely changing the course of humanity?
That's a
question.
Yeah, spiritual. It's like a spiritual question. That, I mean, I obviously I wouldn't be able to answer that, but I think that's a very valid point. I think that's really the heart of the issue of most of this, and most of progressive science in general is, I agree with you 100%.
I mean, in terms of ITER, like I say, incredible engineering is being done there. I genuinely believe, and increasingly believe, but I've said this for the last couple of years, I cannot see that is how the sun works. It just, I can't see how it works like that.
Right.
And you know, yes, it works in the case of maybe an H-bomb, but maybe even the H-bomb is not working like that.
Yeah.
You know, is it layered assumption onto layered assumption, and they've built in something that kind of will produce an outcome, and the outcome will potentially produce a net energy gain, but is it practical? I don't think it is. And I think Bill Gates said this himself in 2010. He has his own company where he's looking to burn like nuclear waste.
Yeah.
And he says the biggest problem is the neutrons that come out, and they make everything, you know, really difficult to handle later down the line. Even when you're trying to get rid of nuclear waste, you still end up with a hot thing at the end.
Right.
and he says that his neutrons are many orders of magnitude less energetic than those that come out of hot fusion.
Right.
And so, you know, and it's interesting. Since I have mentioned Bill Gates, he has started looking, you know, under the table, not really under the table, but if you know what I mean, under the radar, let's say it like that. He is investing into cold fusion, as it's called. And I think probably that shows his intelligence.
Yeah, he's a very open-minded individual. So, you know, and he reads a lot. It seems like from his biography and all that kind of stuff. So that's healthy. I think there's a lot of people. I honestly believe there's a lot more people like that in the world. There's a lot more good out there. It's just the good needs to be represented. You know, it needs to be marketed instead of money, right? It needs to be like what we're happy about, what we love to do. I think should be put on a pedestal more. You know, right now we see mainstream media, it's just all this negativity, all, you know, people killing each other, yada yada yada. Yet if you look at the data collectively over the years, I mean, we're living in probably the most abundant time, you know, for the majority of the planet with the largest population ever.
There's abundant and drawdown. We're certainly more effective at drawing down the resources of the planet. So it may feel like abundance now. But
people surviving too and everything, like just quality of life has gone up in general, especially since we have, you know, per population, you know, and don't get me wrong, I am very much privileged, you know, being who I am, and you know, I would not want to be in 7 billionth place, you know, on this planet. Like I couldn't even imagine, but in general, I think that we're probably better off than we have been, you know, 2,000 years ago, 3,000 years ago. But, you know, then it gets murky.
Yes, I would say probably that's true on a materialistic point of view and on a life chances point of view.
Right.
You know, if you go back to 120 years ago, you're unlikely to meet your 5th birthday or whatever.
Right.
Now, no one expects to have 2 children and not see them graduate.
Right. We won't go into this. We won't go into the spiritual side. Yeah, that's
on a spiritual level.
Yeah.
I think we're probably pretty much toast.
Yeah.
You know, there are people out there that are in connection with their spiritual side, that they understand the importance of that. I did lose it for a while. I would say that I regained my spirituality probably in 2017. I would say.
Yeah, I mean, and I think that's the biggest. Well, if you look at it with probability too, though, there's a lot of spiritually minded people aren't as vocal a lot of times. They're content and happy with themselves, happy with their lives. So you may not see it very much. And with the amount of population, you know, who really knows? But yeah, I agree with you as far as the Western world goes and what we focus on in our media and stuff like that. I agree with you for sure.
Can I hold on? I think I have my better half calling me.
Okay, all right.
No, wait.
So yeah, if you guys have any questions, Jim, yes, I did say pedestal. If you guys have any questions, feel free to ask. Yeah, I appreciate you guys who are watching live. It's awesome. I'm trying to get more of these together. I'm so grateful that Bob was willing to come on. But please, if you have any questions, like as far as your experiments or what you'd like to do or what you'd like him to answer, feel free. Feel free to speak up, to type up, I should say.
Sorry about that.
No worries.
It was a UK EU time, and there was a time difference of an hour. So my better half thought I was finishing sooner than I am. So let's hope that's okay. We're just getting started.
Yeah. So
I didn't even have time to shave today.
Yeah, neither did I. It's Sunday.
It's got more of the mad scientist look going.
Oh yeah, exactly. It's rugged. It's rugged. So what do you think was, like, in history from your research? What do you think was like the first example of LENR or touching on that phenomenon?
I think it was the first sun in the universe.
Besides nature, I'm talking about our cognitive grasp of it, like our awareness.
I think probably the first people. So are we talking pre-ice age or post-ice age?
Oh well, we don't know much about prehistory, so yeah, let's go. But the prehistory thing, that's a whole nother can of worms. We won't go down that rabbit hole, but just in general.
I think probably the first example of LENR was with alchemy.
Okay, so do you have a reference, like time frame wise, or any certain culture?
I don't know. Some people say it's thousands of years old. Some people say it's 5,000 years old.
So you're saying like Egyptian, like Baghdad battery, that type of stuff, like still kind of prehistory. What about like in modern, our modern grasp of history? Like what would you?
Well, I think the first biological transmutations, if you look at Jean-Paul Bavarian's book, all fusion in all its forms, or I think in there he cites references from 1798.
Okay.
I think the first person to probably realize that he had, or was at the time, but maybe post it he realized, was Tesla, and that was when he was demonstrating his carbon button lamp. I think it was in, I don't know, 1891, 92, something like it. It was in the late 1800s.
Yeah.
And he did it in America, and he came to I think the Royal Society and presented there as well. Because it was carbon, silicon carbide, or whatever, I think he would have seen a spread of elements being synthesized, and he was also synthesizing Röntgen rays, which later we call X-rays,
right.
Probably in the West. They call them Röntgen labs here in the East Europe. But,
yeah, more it's traditional. It's more part of the roots, right?
yeah, but X-rays, and I think if you go to, I think it is in Serbia, if you go to the museum in there, they have some examples of exposures that he did. I think, oh look, I can see my bones.
Yeah.
So I given the fact that he was seeing those X-rays and I think probably Tesla was first. And I recently did a blog and a video based on Tesla's, I think 1932, like one of the latter
last things he said.
Yeah, he said something about that he was doing radiation, like changing the radioactive rate of decay, and he talked about this and published it in sort of,
I read that article.
93 to 6 or 7, something like that. Around the time that electrons were being discovered, he was actually publishing articles around this. So I think without a shadow of a doubt, it would have been him. When it comes to loading hydrogen into metal, it was a guy called Thomas Graham, FRS, and he was the first head of the Royal Society, and he found in the
1930s?
No, 1870s. I think
oh, wow.
Even before, long before deuterium and neutrons were discovered, that the maximum amount you could load any element with hydrogen was hydrogen into palladium.
Yeah.
And basically that's the level we actually seem to be able to load it even today at the best levels. And he said the only way you can really load it is to make sure you have no nitrides or oxides on there. For those people that don't know, typically in cold fusion or low energy nuclear reactions or condensed matter nuclear science experiments, one of the ways to do this is you take a transition metal typically that is able to load hydrogen. You load as much hydrogen in there as possible, and in the case of titanium, you're more flexible. In the case of palladium, you really want to load deuterium. It seems to work with deuterium better, that's essentially what I'm talking about there. So have you got any questions right now that want to be asked here?
No, not just
Jay Price says heavy water isn't that expensive. No, it isn't. I actually have some in the other room, but it depends on the volumes you want, and you really don't want the oxygen in there, so you actually only want the deuterium, and it's the tritium that's really, really unpleasantly expensive. It
has a short shelf life, so to speak, right? It has a decay rate,
tritium, like 10 years or something like that.
Yeah.
So you need to manufacture that. Now, one way that they look at doing that is that the neutrons that are all bad and make your reactor hot, you have a lithium blanket, and lithium has a very good high level of barns for stopping the neutrons, and when the neutrons go in, they actually synthesize tritium. And so the idea is that your lithium blanket would actually breed the tritium that you need in combination with the deuterium.
That's cool. I did not know that part of it. Yeah, yeah, that's interesting. So, what experiment do you think? What experiment interests you the most right now at the present moment? Any in particular that you know?
What you mean
In the field for
in the field?
Yeah, for LNR.
I think experiments that are able to demonstrate transmutation. I think the challenge with excess heat is that, yeah, it's always able to be criticized, and so you get into this kind of whole argument about, did you have the calibration right? Did you use the right type of way of measuring the temperature? Did you measure your input power correctly? Who are the instruments calibrated?
Right.
Are you the right qualification to know that all these things are correct?
Yeah, that's been a challenge from my research for sure.
It's absolutely endless.
Yeah.
And so, there's always a way to stop these things. Then there is the transmutation to other elements. Now, this is a much higher level of evidence, but then you always get these things like Andrew Johnson calls them Agent Smiths, and it's kind of like you get these people, they pop up and they go, it's not possible, go and read a textbook, you cannot transmute elements,
right.
It's not possible.
Right.
And it's like, hold on a minute, are you alive? And they go, yes. Right, do you have any calcium in your body? Yes. Do you have any carbon in your body? Yes. Both of those are transmuting right now in your body every second of your life.
It's true, biologically, yes.
Well, no, not just naturally.
Yeah, well, I mean, that's nature, is to take the base elements and make more.
Nitrogen,
right. Yeah. That's we wouldn't exist without it. We know it. We know that nature does fuse elements, and there is transmutation, and things are constantly changing and evolving, because otherwise we wouldn't be here, right? So we know that for certain. So I see your point, but whether that comes across in somebody.
In both of those cases, they're emitting a beta, and in the case of potassium-40, it can go one of three ways, but it predominantly emits a beta and goes to calcium-40. So, sorry, but if you have potassium in your body, rather,
right.
which we all know
we do.
So potassium-40, one of its main decay channels is by emitting a beta, and that goes to calcium-40, and the carbon-14, which is the basis for radiocarbon dating,
right.
is going to nitrogen-14. So these are things that are going on all the time. So transmutation is real; it's happening in every single living thing on Earth.
Right.
So let's get that out of the way. So
I think it could be that just some people have such a specialized approach at looking at science, where it's just in one skill set rather than looking at a larger picture. Maybe that's one of the big problems that a lot of people have. It seems so empty because they're not looking at it with that large scope.
Well, you're absolutely right. And so when I was at Aarhus University, I had a moment in time where I really realized that not only that there are disciplines that are separated and they have their own lexicon and so forth, that they also have a huge universe between them. And so if you're looking at the chemistry lab, because they're using borosilicate glass vessels like this Cafola cup here, and it starts to soften at 300 degrees, or they're using maybe other types of apparatus containment, they really want to, for industrial processes, they want to have most industrial processes occurring below 300 degrees centigrade. Preferably, definitely not above 600 degrees centigrade. You should start running out of materials that quite quickly that you can actually contain things with. So they like to look for catalytic processes. That's a whole other question. What is a catalytic process? But anyway, so they're in the sort of 300 degrees centigrade. And then when you go over to the physics lab over the road, they are starting at millions and millions and millions and millions of degrees centigrade.
There's a lot in between that they're kind of skipping. Yeah.
That no one's looking at.
Yeah.
That's not true. There's a guy called, I think, Kazagi, and he won the Preparata medal in Sendai ICCF 21 a couple of years ago. Or, in fact, that was last year, was it? Anyway, in Sendai ICCF 20, rather, that was a couple of years ago. And he actually looked at energy levels below the sort of 4.5 mega electron volts that your typical sort of cyclotron will speed up your proton to.
Right, to break the Coulomb barrier, right?
Yeah, to smash it into a piece of lithium and to conquer a Fulton experiment. Up to millions of electron volts or whatever.
Right.
And he actually found that there were resonances where way below that you could achieve nuclear effects. And in fact, there's one researcher, the Lipinski brothers, that have this type of fusion. I think it's Quantum Gravity Corporation or whatever. But anyway, they were actually looking at, and I think it was 222.1 electron volts. I mean, you could use a domestic power supply to accelerate something to this energy. They were able to get protons to interact with 7 lithium. So the jury's still out on that. There are groups that are looking at maybe replicating that. One of them actually discussed that, who's I think working at MIT, and they've actually got a piece of either their apparatus or an analog of it, and they did a lecture on getting that up to spec, and I think they're going to investigate the Lipinski proton 7 lithium fusion experiment. But certainly the Kazagi work has shown that this immense area of temperatures between the chemistry department and the physics department actually has areas in there which are open for exploration that could actually yield outcomes. And so, and when you go to the chemistry physics department there and you say, well, it would appear that some of these systems that have been reported on historically, they're actually, how shall I say it? They are transmuting matter at a faster rate, i.e., so the radioactive decay of one element to another is the decay rate is increased.
Right.
And actually, I had someone at that university say to me, well, this is just impossible. And
that's what Bill Gates is trying to do. I mean, that's right, to go full circle back. I mean, he's essentially trying to use. I believe his approach is with fission, right? But
well, with fission, you can effectively burn things using the neutrons that come out, making unstable element isotopes that then decay, and then if they're still big enough to be knocked into an unstable regime, then they decay, and so on. So it's called nuclear burning.
Right.
And what you do is you end up with stuff that's got shorter half-lives or less energetic or whatever. But you're gaining energy during that process. So what we are looking at, or seemingly looking at, and it's very interesting because it would seem to be that it's atomic hydrogen that's absolutely key to this process.
Seems like it.
Well, in the case of nickel hydrogen systems, you're looking to catalytically split molecules of hydrogen, H2 or D2.
Dihydrogen,
catalytically split those so that you have radicals. So you've got a proton with no electrons, proton with 1 electron, and protons with 2 electrons. So you've got the various thing there. But the proton with no electrons is, proton with 1 electron is kind of like atomic hydrogen, but proton alone then seems to be able to do some really, really interesting things. And there's a guy called Langmuir, and I think in the 20s or 30s, and he produced this thing called the Langmuir torch. So you have hydrogen coming out. There's an arc discharge that is, by using the arc discharge, is creating atomic hydrogen. And he, as far as I understand it, reported transmutations, but then he was asked to walk that back and retract what he said.
Right.
Now, if you bring that right up to the current understanding that we have right now, there's this guy who I had the pleasure of visiting in Japan, and he invented this technology in the late 1990s, but actually got it patented in 2001. And he's called Roishi Namasa, and he produces this vibration system and this gas, and this gas is it's kind of like the gold standard of Brown's gas.
Right.
Brown invented this thing in the 70s or something, even before that maybe.
Yeah.
But he demonstrated that it was able to remediate or change the decay rates of isotopes extremely, extremely quickly.
Right.
So, for instance, the case of cobalt-60, and in the case of americium-241, the sort of thing that in the US you'll have in your smoke detector, he was able to take americium-241, put it on a ceramic block, put some aluminium shavings and some iron shavings in there, put on the Brown's gas, which is basically oxyhydrogen gas pre-mixed.
Right.
Ostensibly stoichiometric, the same number you have in water in the gas,
right.
Hydrogen and oxygen, and a few seconds exposure, and then you got this flash, and like 97 or whatever percent is removed from the americium-241, which is just absolutely crazy. And this was demonstrated in 1991. So
right.
The implication is that you can massively change the decay rate. Now it's interesting because in a YouTuber challenged or had some questions about a reactor called Sapphire, which was designed to test the electric sun model.
Yeah, we were going to get into that. Yeah, electric universe and all that stuff, definitely.
Well, basically, the guy Montgomery Charles mentioned in that particular video that at MIT they have shown that using atomic hydrogen, they could massively change the decay rate of hydrogen. So here you have a whole bunch of scientists that they're ancient Smiths, and they're saying this is impossible. And then you have MIT that's saying this is possible. But by the way, Brown's did this a long time ago, and if you look, we've already published on our Facebook channel, I think in the 2000s, at some point in the 2000s, or it may have been more recently, the gas from Roish Amasa, this Amasa gas, was tested, and it contained 0.2% of atomic hydrogen. Now, it might not sound a lot, but this can be stored for 10 years, and then you can just get it out, and you can then, in theory, do this radiation remediation. And so I wanted to talk about, coming back to the excess heat situation. It would seem that when you get a lot of excess heat with these kind of low energy nuclear reaction systems, it starts to cause reactors to fail. And when you've had a failure, it's very difficult to say that the elements that are in there are not contamination, because the thing melted down.
Right.
Took half of the apparatus with it.
And sorry to interrupt, but that's honestly why I don't go towards that approach, towards the hotter of the cold fusion approaches, because of that reason. I think that if it's contained in a medium that's dense enough to be able to handle the interactions like a aqueous cell, I think that is my approach is more that direction, because I'm worried about if there is a breakdown, like the contaminants and how it's interacting with the other elements in the reactor itself. I'd like to really just narrow it down to just a few components and keep it simple. What do you think about that? Do you think aqueous is not the way to go, or?
Well, I think when you have a fluid in contact with a solid, both of those things have high electron density. So they are, in a way, condensed matter. The beauty of a fluid is that it is not locked in place, and it can take away thermal energy.
So here's hold on one second. I got to jump in, because think about this. What happens when you make that fluid turn into a solid, like superfluidity? There's a research paper that recently happened. It's I think it's in the range of 40 C. Sorry, that was my dryer buzzer. In the range of 40 C, there's a like an organizational pattern that happens in water. I can link you. I don't know if you've read it. I can link you it, but then it's condensed on condensed, and you're channeling the thermal and hydrodynamic motion across. So like breeding, almost like what hot fusion is trying to do with their plasma, in a sense. What do you think about that approach? That's kind of an approach that I've been experimenting with.
I think water is very clearly a very interesting thing. It's necessary for life. I don't think anyone doubts that. And I think what's going to happen in the next 10, 15 years is people are going to understand a lot more about why it's so necessary for life. It's a medium through which life can exist. It's a medium that life needs in itself. It's in everything you eat, and to a certain degree.
And it has an abundance of elemental number one, hydrogen, like we talked about, and it's
yeah. But I mean, what Roish Amasa has found is that there are water clusters like buckyballs within its material, and maybe they are able to store. They certainly appear to be denser, like it's like more solid water.
Right.
But in fact it's in the form of a gas. But
right.
when you burn it, it ends up being water again. But is it the same water? I don't know.
So that's the two things I'm like I've been going over my mind a lot too. and especially with Amaza, like it's really interesting because how he produces the gas, what temperature range is he getting that water when he's putting the mechanical oscillations into it? What temperature range does it go up to? Or he has to preset it to a certain temperature, right?
So what I will say is that, and I have one of the vibrator plates here, but people can go on the MFMP's YouTube channel.
I highly recommend it.
YouTube channel. But this is one of the plates. You can see from the size of my hand roughly how large that is. And what he does is a non-direct coupled vibration system that's vibrating. In the case of the hydrogen generator, it's vibrating at around about 60 hertz. But in the case of the transmuter, it's vibrating at like 3 times that.
Right.
But that's the fundamental frequency. And it's kind of vibrating like this, it's vibrating like this, and it's vibrating like that.
Yeah.
And within that, you've got modes of vibration this way. And because of the way it's held, it snaps as well. It kind of like cracks like a whip. And so you get all kinds of resonant modes with sound on here, and you can see that where those resonant modes do some level of interaction, this is my interpretation, that you are getting some kind of energy concentration, which allows, when you look at these under the SEM...
Like cavitation, right? Because you're making...
Is it interacting sound waves in here that are causing an energy concentration, like a wave this way, a wave that way, a wave that way, a wave that way,
right?
And it's causing such an energy concentration which is resonant that you get to a point where a nuclear event causes the cavitation bubble,
right?
Or are you saying a cavitation bubble causes a nuclear event?
See, that's a great question to ask. That's really I think you put it very simply. That's the question that we all have: is it from within or from mechanical? Like, I almost look at it this way, like in nature too, you look at it with balance, right? Anytime that there's a void of energy, like we try to go to absolute zero, right? With using laser, standing node, oscillations or frequencies, right? To create these pockets of supercooled area. And we can never go to absolute because energy is always trying to rush in. It's always trying to come in, even no matter how much we block it. So I think that goes into that very same statement that you said. That's what we need to sort out. Right, I agree with you.
So if there's nuclear events going on just on the vibration plate, is it setting up a type of condensed matter, or is it the cavitation bubble that's causing the re-entrant jets,
right,
of the LENR and those kind of ideas of Moray? And are they then shooting, as Moray would say, through the electrolysis plates and self-organizing these water clusters and as essentially it's not hydrogen coming off one side or oxygen coming off the other side. It's supposedly this channel in the middle where some other type of version of bubbles appear, and is it capturing those?
Yeah,
and
like a toroid, or like the classic pictures of a black hole type of deal, like where the center of mass, so to speak, to put it simply, is where all like the energetic happenings is going on.
Yeah, so basically this gas is synthesized, and it seems to have some of the properties of Brown's gas. And I didn't really know what the properties of Brown's gas were, but one of them I did know because I'd recently researched it, because I was looking at radiation remediation. So the idea is if this thing gets really hot and it mashes up all the elements, and at the end of the process you get a load of stable elements, well, can we use this to take already nasty waste and learn about the process whilst we are dealing with the waste? And when we know we've dealt with the waste and so on, we'll really understand LENR and how maybe it can be contaminated and so forth. So it was really exciting. He wanted me to mostly look at the plates, and that was great because I could learn about what really was going on the plates, and so we could establish that it wasn't low frequency that was only there. I mean, there was definitely low frequency, and it was the fundamental. It was most of the energy. But
right,
23 decibels below that, there's a very large amount of ultrasonics going on.
Right.
Is that coming from the resonant on here and then a
sub
event, or is it coming from a collapsing crack of a cavitation bubble? whatever.
Right.
The point was that we established that more interesting things than were originally thought were going on. This would explain why in the 2000s, when he had sent off some of his water, which was deionized to start with, and he sent it off to be tested, that he found a large proportion of the lighter elements, up to kind of like all the ones that you would have in your body, in the water that was exposed to the subtle vibration. And this might explain, or it certainly explains for me, why the fish that he has in his lab, and he sells these systems to people that are growing fish and eels for consumption, they grow much more healthy, they grow bigger, they grow faster. And my view is that it may be actually creating bioavailable monoatomic elements. So it's actually synthesizing elements. And I did a test, and we have this calculator that we've developed at a site called nanosoft.co.nz. And if you put into one of the Cascades 5 Lite, if you put in 1H1H and you put the energy levels to 0.1 MeV, 0.1 MeV, and you set the reaction recursion level to 7, it will come up with pretty much every element that you have in your body, starting from just protons and protons. And of course, with water, you've also got hydrogen that you may be able to play with as well. Right. So you're ending up potentially with a system that would appear, at least on a scientific, we start off with deionized water, we flap the blade around in it. There's no electrolysis going on, by the way.
Yeah, that's what's surprising. Right.
No electrolysis going on. So what happened is that, you know, he was trying to make water clean. And I guess, and I'm not saying that this was his thinking, but I guess that if he's trying to say I want to purify water, but actually what I'm ending up with is a load of elements that weren't there to begin with, people might worry about that. But anyway, that's apparently what was happening. And that information was personally, I would have liked him to have come out with it at that point, right, for his own good at that time, to get it on the record. But what happened after Fukushima, he thought, well, if this is actually transmuting elements, maybe it could transmute elements and deal with radioactive water from Fukushima.
How are the plates treated before he goes through the process, though? Do they go through like some type of ultrasonification bath? And
normally they're just normal stainless steel plates cut into shape and put in place. So I know with electrolysis and HHO generators, they will do chemical treatments or sandblast them and do other things to create places which would have maybe catalytic or energy concentration effects on the surface, or for nucleation of bubbles or whatever.
Right.
But just these things are really quite rudimentary and simple. And so the idea is that he was thinking that maybe as it seems to be creating elements or manipulating matter, perhaps it will do what, and this is my view, is that we already know nature wants to go from unstable to stable, because that's what radioactive decay does.
Right.
It starts as unstable things, and over time, which could be a long time, by the way, it ends up with stable. But if this is able to synthesize elements in a very fast way into bioavailable elements, could it possibly do the thing the other way, like encourage it to unsynthesize? If you know what I mean?
Right.
But do it in a safe way. And so he took a plate system in a concealed container and put Fukushima water in there. And with a TV crew, I'm told, I believe, but I don't know, I don't have the facts, but this is what I'm told. There were TEPCO engineers, engineers from the Nuclear Authority or whatever, and politicians. And in 13 days, it removed one half-life from cesium-137, which should be over 30 years.
Right.
And in a further 17 days, it took another roughly a half-life. So 2 half-lives were gone in 1 month instead of 60 years plus, right?
That's pretty impressive.
Absolutely ridiculous.
Yeah, that was. But unfortunately, though, that's mired in like a rumor, right? Unless do you have actual documentation of that process?
The tests were done, and I've published the videos on our channel of the data.
Okay.
But for some reason, they didn't. The TV crew didn't publish their data, and they didn't take up on his offer of supplying these things to fix the Fukushima radiation water. Now we've got 1.2 billion tons or something of water that there's an argument between the Japanese and the South Koreans of should we be poisoning the Pacific with this, which, by the way, you probably swim in, and you don't want all that water coming your way.
In Oregon. It's probably yeah.
So the point is that it's frustrating. This was done in 2012, and here we are in nearly at the end of 2019, or coming up to it, And why isn't it being done? Well, maybe, but just maybe, the agent Smiths popped up and they couldn't believe that this could happen, even though it's like, don't believe your lying eyes. Don't believe them. Don't believe the fact that this sealed chamber, the radiation changed. Don't believe it, because it's not possible, because there's a textbook over there that tells you it's not possible. And if you don't know that it's not possible, go and read the textbook.
Yeah, okay? And then you go into, like, you're falling into politics and spirituality, because in a way, because look at it like this. I think it was Gandhi said, right, and this is very spiritual leader type of person, but he said, first they don't believe you, then they deny what you have to say, and then eventually it becomes accepted. But it takes time, because people have to be more spiritually inclined to it. They have to relate to it somehow. I feel
to give them credit and some leeway. Firstly, you have people saying that transmutation is not possible. Sorry, it's happening in your body every single second of every single day.
Right.
Anyway, and that is decay. It's unforced decay. And the idea that you can't force a system to do what it naturally wants to do anyway is a little bit bizarre to me. But so you have this system, and effectively, what is surprising about this is that it smacks of a bit of what Yul Brown had done in 1991 with his forcing of the decay, making the faster the decay rate in cobalt-60 and americium-241. So you have two systems here that are doing a similar thing in one respect. And the other thing is that we know already from cavitation bubbles that in the case of cavitation bubbles, they have been able to synthesize elements from the work of Leclerc and his partner, Nanospire. And this is where they were either using like an aluminium drum with holes drilled in it and spinning around inside a PVC pipe, and don't want to do it, it'll kill you because of things that it emits. But it was synthesizing all of the elements in the periodic table and even some transuranics. This is pushing energy in the system. This is maybe tickling the system so that it decays, does what it wants to do naturally. And so we already know cavitation bubbles can synthesize elements. So my view was, when I went over there, is I know he says that he's only vibrating at 179 hertz maximally.
Right. That's the carrier wave, the overall mechanical carrier wave, the kinetic energy.
That's what's forcing the bulk of the system.
But that's not necessarily.
I thought that this has to be producing cavitation bubbles, and so there will be some ultrasonic signatures of that.
Right.
So I prepared a hydrophone.
They're phonons.
Sonic things, and within the first day, within the first hours of getting access to the system, we already knew it was producing ultrasonics.
Right.
From the hydrophone and from an external microphone.
It's phonon vibration when it's like. Yeah. Exactly.
And so we already knew it's producing ultrasonics. Then, after some negotiation, we got access to look at a plate, and I was handed the plate, and in the light window, with approximately 2.3 seconds, I don't know, I'm joking there, but maybe 3 seconds of looking at it, I could already see the marks on the plate. So I already knew, but it was already telling me that it's not just all over the plate, it's at points at which it's favorable for those things to occur. Under the microscope, it became obvious that was cavitation involved. And in the slow motion videos, you can even see the bubbles going around and moving around. I've already seen these things in India when I was looking at Suhas Ralkar's work, who is an expert in ultrasonics, and it was admittedly producing vast amounts of cavitation. So I knew what I was looking at. And so we knew there was a mechanism, and the mechanism is cavitation. That's already been demonstrated to transmute matter.
Right.
So therefore, they now had a mechanism, and so they were actually doing this experiment where they had deionized water. They were adding 5% deuterium oxide, so heavy water, and then they were adding magnesium chloride into the water. And then they did some water purification tests, like you would want to do if you wanted to find out whether you were getting rid of nasty things in your water, and because for a fish farm, for instance.
Right.
So you had all these water ion tests, and one of the ion tests they were looking for was for iron. I mean, not ION, but IRON.
Right.
And I said, this is great. It does look like it's done synthesized quite a bit of iron. The problem is that there's iron in the steel plates, and if there's cavitation and it is digging away or channeling that thing, it may be just stripping out iron from the surface.
Right.
And then I thought, well, okay, let's go and look at the calculator. And it turns out that magnesium chloride makes iron when it fuses together. And so it's kind of like, and I need to check that. I'm just doing that off the top of my head. But whatever they were using ended up synthesizing iron preferentially. And so by the time the Nikkei science reporter staff writer came round, that's one of the leading newspapers in Japan, in Tokyo. By the time that came round, this was halfway through day 3. We'd already found out the mechanism. We already found out, blah, blah, blah. And we had some demonstration that it might be doing what it said on the tin. And it's just a shame that this couldn't have been done in 2012. And then rather than having 1.2 million tons or whatever it is of toxic water and running out of space to store it, they would have a lot of water that I wouldn't say drink, but certainly you're not going to make a lot of toxic tuna.
You could put it. You could actually put it into the ocean without it being as harmful, type of deal.
Well, essentially not harmful at all.
Yeah, right.
And then there's that, and then you have the fact that is the atomic hydrogen being synthesized at this point, and that's doing the work, and that's creating these synthesized elements. And is that being packaged into these bubbles that's produced in the electrolyte? And then that's synthesizing this gas called a Mars gas, which seems to have some properties, as I said, of Brown's gas. And so my concept is that essentially what it looks like is that nature is trying to pack things into a very small box. Okay, and the reason is because you tend to get elements that occupy less distortion of the physical vacuum out of the process. So if you take 2 deuterons, they occupy, let's say, one unit of space-time. Helium occupies 1 unit of space-time. That's 4 helium. In fact, 3 helium occupies 1 unit of space-time. So the reason that when you merge 2 deuterons together, you get a huge energy gain is because you are releasing that energy that's released from less distortion in the structure of the physical vacuum. And so if you just take that alone, that's already telling you what nature wants to do. But just look at what the many sort of what you have in the center of the Earth. It's like supposedly iron and nickel. Well, iron 56, nickel 62 are very, very
the balance, the universal balance as far as matter. Yeah,
they're very well packed arrangements of nucleons, i.e. there's a lot of nucleons occupying a very little amount of space-time relatively to most of the other atoms in the periodic table, the nuclei. And
I think I was looking at the abundance tables of stable elements in the universe, and iron's like dead smack in the middle. So I totally know what you mean.
So essentially, if it's trying to pack it into a small box, then one of the classic transmutations is where you take carbon and you take carbon and it makes iron. You take carbon, a couple of 12-volt batteries, and this is a guy called George Osawa. He was a Japanese guy that came to the US. He invented the macrobiotic diet, but one of his other things was doing spark discharges between carbon on carbon. And he was finding iron in there. Now he was also finding other elements that are necessary for life. And essentially what you've got there is lightning and carbon. You've got an intense electron density increase there. And you're synthesizing iron. Now, one path to iron is you're kind of like you're doing it in air, so you've got nitrogen. It's 78% of air. So carbon and nitrogen fusing, they're making aluminium 27. 227 aluminium atoms are making iron 54. And so you are taking 4 nucleons, 2 carbons, 2 nitrogens, and you are making 1 nucleon of iron 54. There's a guy called Bockris who was worked with Flieschmann, and a guy called Sundaresan, and they replicated this work, but they have a different take on it. It's 2 carbons and 2 oxygens are fusing together, and they're producing iron 56 and 4 helium. So the work has been, this particular work has been replicated by many people.
Right, and
so,
well, even foundation is in Tesla, like his carbon button lamp, right?
Exactly.
Yeah.
So he will likely have seen synthesis of elements, because he puts it in a near vacuum. Maybe there's some noble gas in there, but let's say it's a near vacuum, and he's got a silicon carbide. He's got silicon and carbon, and then whatever the insulator is for that carbon button lamp, and then he's getting all these other elements. Where do they come from?
Right.
You know. So there's a lot to be given credit to Tesla. Now, essentially, if it's packing into a small box, then when you get elements beyond nickel 62, they start to become less efficient. Let's imagine that they come long and stringy. They're not in a little sphere, and so what you do is you need to break those up, and the broken part actually occupies less of the space time than the bit connected together. So this is what happens when you take uranium-235, the most beautiful nuclei in the universe, in our universe, and you split that in two, and there are probabilities of the way it splits, but typically some of the elements you get out cesium-137 and strontium-90, and these elements, because of the organization of the nucleons, occupy less space-time. And so it's trying to find solutions to this where the products in fission occupy less distortion of the structure of the physical vacuum, and the balance is energy that gets released. And this is even true of chemical energy. If you look at the work of Stoyan Stark, he even goes and argues that. And so whatever the energy is coming from, it's through lowering the amount of space-time distortion. So now,
like the amount of data packed into a system. If you look at it in that terms of data,
data package, it's
right.
more condensed matter.
Right.
It's trying to condense matter. Actually, condensed matter nuclear science is a really good name for it. And so let's say you have a structure, whatever the structure is, and it's able to pack things into a really, really small box, and it wants to put in small box. And like, if everything's coming in, it wants to go in, and it's trying to get it more into this small box, because this structure doesn't want to grow, but it can still throw things into the middle. Well, there's 2 concepts of matter here, and it's like 2 kind of types of matter. It's like, if you have integer spin, then you're a boson. If you have non-integer spin, you're a fermion. But fermions, like electrons, unless they're in a Cooper pair, they can't occupy the same space-time. And so they have to be apart from each other. But and that's the same with nucleus. If a nucleus is a fermion, it can't occupy the same space-time. So if you take 227 aluminium, they can't occupy the same space-time. But if you're squeezing them, they're going to go, all right, I give up. I'm going to try and organize myself into a nucleon where we can live in the same space-time. So if they fuse into iron 54, they're then integer spin, and then iron 54 nuclei can occupy the same space-time.
Right.
And so you get something that has a lot of matter in a very, 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 very small space. Now, it kind of looks a bit like a black hole.
Yeah. So that's... So and
or is it a black donut?
So I'm gonna go into some. This is some really deep, because I really want your perspective on this. This is some really deep
I need
science.
to explain.
Okay, all right.
Okay, go on. Ask me a question.
It will go into that. I think it ties right into this. So you're aware of like a helium superfluidity, right, and condensed matter physics, right? Have you researched at all hydrogen superfluidity or metallic hydrogen, as it's called? And because I personally have tried, I've made it a quest for the past couple of years to look at every paper I could, and most of them are you have to pay to learn, and like it's not cheap either. So you haven't.
Sci-hub.tw.
Okay, thank you. I appreciate that. Yeah, because I mean seriously, like.
SCI-HUB.tw.
Okay, cool, excellent. Yeah, okay, so because tying into what you're saying, like, you know, there's abundance of what you're talking about, iron, and then obviously hydrogen is also incredibly abundant in the universe, and so is oxygen, you know, the elements that make us, basically. And I find it fascinating that there's this talk about gravitational forces and stuff like that and how matter plays into it, and yet there's no talk about condensed matter physics except for like a very small few, I think, in black hole research. Very small. There's a Spaniard guy I know who's very heavily involved in it, but what's your take on that? Like, and how does it? Do you think that it's part of like the electric universe? Like, what I guess the best question to ask would be like,
okay, let me answer your question. So you're saying are different states of hydrogen clustering or whatever, are they playing a role? I will say that if you look using sci-hub.tw at the work of Matsumoto, he was a Japanese nuclear expert, worked at Sapporo, the university there.
Right.
And he started doing and replicating fusion experiments in 1989. By, I think, 1990, he had published his first theoretical understanding of what was going on. And I think in 1991, certainly by 1992, he had shown and had written specifically that there are basically like a condensate of hydrogen. And
right.
so in one phrase, I think it is saying that nickel is not able to absorb hydrogen, but what happens on the surface, it forms this condensation, it forms this incredibly dense thing. And he actually showed SEMs of frost, of what he calls frost of hydrogen and droplets of hydrogen. And he specifically says that this form of maybe atomic hydrogen is then able to transmute matter in a way that it's going proton by proton. But it seems
subatomic.
Also, well, you fire a proton into most elements and it'll progress across the periodic table.
Right.
If you keep doing it. And so this is the theory of one guy called Francesco Piantelli. And if you look at his patent, which is valid, it's a cold fusion patent, which is valid till 2032. The guy is 86. I saw him last week or the week before. He's rudely clear in his mind, but his physical, the thing that we have to walk around in is not really up to keeping up with mind.
Happened to us all,
yeah. Anyway, I recommend anyone that's interested in this field really need to go and look at the work of Francesco Piantelli. He discovered nickel hydrogen system in a biology experiment in 1989. It was in August 1989, and he had this like brain cell, I think, from a mouse, and that he was studying like what happens when a brain starts to lose oxygen, they start to die. What happens in the chemistry such that, but essentially what happens is that the understanding was that it produces a chemical that prevents the cell from dying. It kind of like shuts up, puts force shields up, right? Mm-hmm. But after a while, the force shields are so strong that if the brain cell gets oxygen again, it can't go through the force shield, and so the brain cell dies anyway. So you have it tries to protect itself, but the protection itself ends up killing the brain cell anyway. And so what he was looking at was the chemistry that changes over time, and he was looking that when you put the oxygen in, it was the drugs that you could put into the brain cell or bathe it in or whatever that would prevent this kind of like ultimately self-destructing process.
Ah, that's very interesting.
Yeah, and so what he was doing is he had a little electrode, and the brain cell was supported on a piece of pure nickel. You don't want to contaminate it. And that was the counter-electrode. And he was doing stimulating electrical discharges through it to keep the brain cell alive electrically. And then he would have it in an oxygen-rich environment so that it would have access to oxygen. And then he would flood it with hydrogen such that the brain cell would start to go through this process of trying to save itself from dying but killing itself in the process. And then he would flood it with somewhere between liquid and gaseous hydrogen, but around about the 4 Kelvin mark. It's basically the coldest thing we can make, without like magnetic spin cooling and cooling and stuff like that. And so he had a cryogenic cooler, and it was a 250 watt cryogenic cooler, and he'd run this experiment a number of times, and outside of the window there's the Paolo Siena. It's like a load of horses going around on bareback and so on, but he's interested in the experiment. And suddenly it started boiling the 250 watts of cryogenic cooling, and there was no electricity attached at this point, and it continues to do it. It's continued to do it. What the hell is going on? There's an itty bitty bit of nickel in there. There's a brain cell, and this is boiling liquid.
Yeah, not what he was even working on. It's not. Yeah, yeah, that's interesting. Yeah,
and so that from 1989 to the current day has been the mystery that he had to solve.
That's funny. So, but it happened around the same time as
Flieschmann and Pons came before, and Flieschmann and Pons weren't only working on what was called by the press cold fusion.
Right.
They were working on other things to do with condensed matter.
Right. Battery systems. I mean, that's pretty much right. I mean,
superconductivity,
right.
potentially antigravity, blah blah blah.
Yeah, yeah.
There's an interview I think in 1994 in Infinite Energy where some interesting things are said, and it's the only point in the 3-page interview where clearly something that was said in the interview was edited out. And it was when talking about these 4 different things that they were actually researching at the same time as LENR. And their moment for Pons and Flieschmann wasn't really we produced a spike of excess heat. In my view, it was what some people call the Flieschmann singularity. And they had a 1 cc piece of palladium, and they were loading it for something like 2 or 3 weeks with deuterium oxide enriched, probably with lithium in the electrolyte and so forth. And nothing seemed to be happening. So I think they asked one of the siblings, or children rather, to go in to just turn the power down. Now, what happens when you turn the electrostatic pressure down? In my understanding, is that the gas that's in there may start to kind of come out.
Right.
And that causes hydrogen embrittlement, and then you get cracks forming, and this sends you through a sequence of events. Anyway, whatever was going on, what was found the Monday morning when they walked in was that the glass in the apparatus had basically disappeared. There was a hole in the fume cupboard, gone through the formica or whatever it is, and the wood or whatever it was that the fume cupboard base was made from. You know, if it's in a chemistry lab, these tend to be like PTFE or something like that. But it could have been stainless steel. I don't know. But it went through that base of the fume cupboard, and then it went into the concrete, and it bored a hole out of the concrete. And in the air, there was this like suspension of incredibly fine particles.
Yeah.
Like, you know,
something I've witnessed personally, actually. So,
really?
Yes, yeah, I did an experiment once that it was pretty intense, and my whole family was like, what the hell did you just do? And I'm like, I don't know. I think I know what I did, but I don't know if it exactly. It involved carbon and it involved aqueous cell. However, it did melt the quartz that was in it. It did have a little metal quartz. I mean, a little where the nickel actually. It turned into a little spherical object and melted into the quartz tube I was using at the time.
Okay.
And it quickly boiled off all the water, and there was a fine mist that smelled like it was almost like sulfur, like brimstone. It was very, very interesting. So
well, I mean, it's the sulfur, as you're aware, is a standard George Osler reaction. It's oxygen 16 and oxygen 16. It's reported as the smell that when you get a ball lightning blow up, you get this smell of sulfur.
That would explain it. I would explain it.
And so we actually took a 10 yen coin at the end of the series of experiments that we did, all live, unbroken, continuous, that's published on YouTube. And it was one of the last experiments. And the 10 yen coin is made of a very small amount of tin, like 2 to 3% of tin. It's made of copper, and it's got some zinc in there. And the Amasa gas, which is the gas that's produced by this vibration plate going through some electrolysis plates in a particular setup, the Amasa gas was exposed onto this for just a second or a second and a half. And Brown's gas, there's a guy called Slobodan Stankovic in Switzerland, and he's actually shown that in his Brown's gas, he has a lot of OH radicals. He's not the only person that has seen something along these lines. There is a guy called Moldavani or something that did some research in the last 9 years ago, and he found that in his electrolysis cells, they were becoming, I think it's more alkaline. It was turning his fingers to soap. So it's actually OH radicals being generated. Now, OH is one of the radicals, or one of the most common interstellar gases, and they can self-maze. Now, if you can imagine, you have gas coming out here, you have a plasma excitation of the gas, and it's got a lot of OH radicals in there. You end up with a maser because it's reflecting off the coin back to the source, and you've got a plasma reflector, just like I was talking about that's latest research.
Right.
Before this call, I said, they've got this research where they've created these lasers that have incredible intensity because they are reflecting off a plasma mirror. Well, you've got the end of the plasma from the burning OH gas, from the burning amounts of gas. Then you've got the coin, which is copper, which is reflecting back. Could you have what it naturally self-mazes OH radicals?
Right.
Could you have a maser? Because when you actually look at the coin, it's like it's cut through with a laser.
Right.
It's like cut. There's nothing on this side. It's not even melted. And this side, it's like a hole through it. But on the periphery of that, there were some different structures. One that looked exactly like a Matsumoto ring, what he would call eventually call an exotic vacuum object. But that's to the side. There was another thing which was a pit, and it looked like it had some little cobblestones in there. And zooming into one of those cobblestones, in fact, you could see it quite clearly at a much higher lower magnification level. But zooming into one of the cobblestones, it had what looked like snowballs running around in snow, like starting small, like you're growing a snowball to make a snowman.
Like little plasma balls, basically.
Well,
running around.
Physical objects that they've started off small. You can see they're small because there's no ball at the start of the channel, and then as it's gone around and it's wound its way round on the top of this cobblestone, it's got bigger and bigger. So the channel's got bigger, and the ball's got bigger, and then for whatever reason it died, and it left a ball which is rich in sulfur, and there's no sulfur, not in the gas, not in the coin.
I didn't know that. So that's interesting.
And the rest of the surface is the stuff that looks like snow is copper oxide. So you actually have the oxygen fusing into sulfur, same as the oscillate. So this is one of the morphological and spatial pieces of evidence which become extremely strong for saying, look, you might say this is contamination, but it's really you would have to go through ridiculous levels of mental gymnastics to say that some contamination got in there and it dug out these channels of the oxide on the copper and ended up with a sphere that's got sulfur in it. I mean,
that's really interesting. Yeah.
Oh my God.
And that's really exciting. I just got a lab space. So I'm going to start carrying out these. I stopped doing the experiments because I did that particular one in my living room. And after that, I was kind of like, I should probably get some, it's just safety concerns with my family and stuff.
Well, Pons and Flieschmann never replicated their singularity. They were so afraid of it. And Piantali went small scale and careful for the rest of his research because you have to respect this thing.
Yeah.
You have to respect it.
And I don't have the proper sensors at the moment. Actually, if you see up on the top, I have a little funding thing for radiation detector. It's like $100, but but why I say exciting though is if I do this experiment and carry it out, would it be okay if I sent you a sample that you can analyze?
Yeah, we'd love that.
Okay,
yeah.
Excellent.
As long as you're open, we're willing to support up to a certain level. But if people want a lot of samples, then we're still willing to do it. But you would have to talk to one of my colleagues, Alan Goldwater, because there is cost involved. There's not just labor. There's.
Oh, I know. I've looked into it quite a bit. Like, I've talked with some people at Oregon State University and stuff like that, and I realize it's not a cheap process at all.
I mean, if there's nothing there, then you saved yourself a bunch of money. If there's something there, then you can maybe go and have it done at another institution that's going to say, "Oh, how did you do this?"
Right. Yeah. So I know I'll get everything written out, and so it can be replicatable and all that kind of stuff. But yeah, I just wanted to throw that out there because this is the first time I think we've formally talked. Face to face.
So the other thing is based on this, it's trying to pack it into a small box,
right? And
that things want to fission, and that there is a very large theory. I'm translating a book by a guy called Alexander Parkhomov.
Right.
And this guy has studied neutrino physics since the late 1980s.
And how's the funding gone on that? Like, have you raised your money?
That's all sorted.
Good, good.
The book is I think 40,000 out of 60,000 words are translated. I wanted to get it done by the end of September. It's going to go into October. But the point is, we've had so much to do that was unexpected. We didn't expect to go and look at Amasa. We didn't expect to look at. I didn't expect to present at ICCF and do 2 posters and stuff. I didn't expect to go and speak at Madison University. So there's a lot happened in between, but all of these things are good. We had an opportunity, because of the way things worked out, to analyze the parts of the inside of the reactor from Alexander Parkhomov, and we found that it would appear that he synthesized lead, which is quite common in high, very well performing low energy nuclear reactions systems. They will synthesize some lead, and typically they also synthesize some tin. Now, if you look at the crustal abundance of tin and lead, they are quite high. In fact, they're often found in together to a certain degree.
Right.
But in the case of lead, Adamenko, a Ukrainian working out of the old Soviet isotopic laboratory outside of Kiev, he was able to synthesize lead very, very regularly from samples that basically didn't have lead in them. In the case of Leclerc, he synthesized lead. In the case of, it would seem, with the Indian that I work with.
Very well documented too.
Right. Yeah, very well. Like 700-page book you can go out and buy now on Google Play, or we can buy from Amazon. It's not cheap, but it's well worth a read. And so Suhas Ralkar in India, he would appear to have synthesized lead. Alexander Parkhomov had synthesized lead in previous reactors. He didn't know until we looked at the core, some core sample from his 225-day reactor, that he'd synthesized lead. He had also synthesized tin as well, and abundant amounts of calcium. And it's very interesting. If you look at I think the top 3 elements are like in the crust are like oxygen, silicon, aluminium, calcium, and so it's certainly in the very top few. I'll bring up some data on that. Let me pull that up in the background to make sure
I'm on it. I'm on it. Top elements in the crust of, in the universe, or should I say in the crust of?
No, in the Earth's crust. I'll just have a look to see what questions are there.
All right, and here we'll switch to this, make it easier to see. Good old Google. So oxygen 46.6, silicon 27.7, aluminum, or aluminium as you say across the pond, 8.1. Iron is 5%, and we can go in deeper if we'd like.
Yeah, I think calcium's pretty high up on that list as
Aluminum,
well.
iron. Here we go. Is it better? Yep, calcium is right after iron. Number 5, sodium 6.
Yeah.
Potassium 7, magnesium's 8, titanium 9, hydrogen 10.
So when building this calculator that we built over the last couple of years, starting with the work of Alexander Parkhomov, we built onto it an understanding of things are trying to go into a small box, but we also need to consider what the most common elements, and even the common element isotopes are. So there's going to be a couple of updates of the LENR reaction calculator, where we are not only, and actually the programmer doesn't even know this now, so if he finds out about this, he'll find out what I've got coming down the pipe for him. But essentially, it's not just the abundance of the elements, but it's also the abundance of the element isotopes relative to other isotopes. What that is telling you, is that in 4.5 billion years of experiments with lightning, plasma pinches hitting the Earth, you are synthesizing these elements, because all that Adamenko was doing was taking a electrode which was flat cylindrical, and it was in a cup, like a cup was put over the top of like alumina, which is a high breakdown voltage dielectric, and then he had a little sample of whatever metal he was testing, and he had a 300 joule capacitor bank that he discharged into this target.
Right.
And the target would then synthesize all of the periodic table elements, and even synthesize elements that aren't even in our near universe, and stable elements that, or semi-stable elements.
It would be like a condensed matter particle accelerator in a way, right? In a sense.
Yeah. So and this is quite easy to understand that this is basically the same as a lightning discharge.
Yeah.
So my view is that you don't need to do 4.5 billion years of experiments. You can just look at the crustal abundance.
Right.
Yeah.
And you can see what's transpired. Yeah.
It's like whatever happened, this was the result.
Yeah.
That's from electrical discharge.
And that's how I like to look at it too in my own experiments, and from the people I've learned from. I mean, so many people in the past, too many to even, I mean, you've said quite a few names, but and it brings me back into like the electric universe theory, and also Sapphire. Somebody brought up Sapphire, and you were talking about Sapphire a little bit. What do you think is the biggest challenge for the electric universe theory to be something of a contender against the mainstream ideas? Like, what do you think is the block there? Why is there so much resistance to? Because it's not discrediting.
I think sooner or later, the electric universe theory is going to have to take on board neutrinos. So basically, there's this simple atomic model. I think it is a SAM group, and there's this French guy and this American guy that come up with this great. I can't remember. It's like, but basically, they're saying that the nucleus only has electrons and protons, and an electron and a proton makes a neutron. Okay, and the clue is when a neutron comes out, it's got like a 15-second or whatever it is, 15-minute, or it's 15 something. Half-life.
Right, very short.
And it decays. But the idea is that it decays and it releases a flavor of neutrino. Now, there is some debate as to whether a neutrino is a Majorana particle, which means it's only antiparticle. And Parkhomov's latest understanding from his neutrino understanding is that electrons at a high enough temperature and a high enough density, i.e. when they're in condensed matter in the form of either liquids or solids, and they're high enough temperature, they will synthesize ultra low energy neutrinos, and these are not the kind of neutrinos that are coming at like 100 trillion per second.
Would you say? Would you
the sun.
Dare to say like they're like vacuum, low? What would it be 0 point vacuum fluctuations? Like something along those lines.
Not necessarily. Let's just stick to the fact that they were shown by Frederick Rains. They were proposed by Wolfgang Pauli, I think in 1920 something. They were and he apologized for predicting a particle that could never be discovered.
Right.
And then in I think 1954 or whatever, it was Frederick Rains and another character, but Frederick Rains got the Nobel Prize for it. Through a beta decay, they established that there was these neutrinos. There was the mass difference and so on. And so I think they had a fission reactor, and they would look at scintillation in a water body or something like that. Anyway, you can go and look up the fact that Frederick Rains, Nobel Prize, blah blah blah. I'll tell you what he did. But anyway, essentially, neutrinos are effectively stable in this form. Neutrinos can exchange energy with electrons, so you can have a neutrino and an electron on one side of the equation, and a neutrino and an electron on the other side of the equation, and they can just shift their energy around, which means they have a physical interaction. So we know they have a physical interaction. What Parkhomov is saying that is the actual massively energetic and highly dense electrons, where they smack together, synthesize a neutrino, which, as I've said, it may be a Majorana particle, so it could flip between being an anti-neutrino and a neutrino, which means it can do all kinds of nuclear reactions. But what's interesting about LENR is, unless you push it too far, in the case of Adaminko and Leclerc, you basically take stable or radioactive elements and you end up with stable elements, and that's the basis behind my interest in exploring the science before we get to making real use of it.
Right.
Is to deal with the mess of
how it's happening. The theory. Well, yeah. And so, what do you think is the greatest challenge for explaining or I think acceptance?
The challenge is they're not talking about neutrinos. They're only talking about electrons. Now, electrons do flood into the sun, Alphen waves and so on.
Yeah.
And they've looked at these things, and the work of Bostic, the plasmoids and so forth, and these things they are real, and so but what Alexander Parkhomov is saying is that you also have, as well as electricity going into these bodies, you also have neutrinos, because neutrinos are affected by two things, or interact with two things: the weak force and gravity. Whatever gravity is.
Right.
Now, the electric universe might have a different view on that, but whatever's causing that, they're getting pulled in. And so if you've got a very large flux of relic neutrinos, I'm not talking about the relativistic ones, I'm talking about ones that have non-zero mass.
Okay.
And by the way, if you're
so not virtual particles, so to speak, like
they're real particles.
Right.
In fact,
right.
The particles he's talking about are supposedly they're about 2 Kelvin, and they are left over from the birth of the universe, if we accept that occurred. Now, the electric universe may have a different view on that, but if you're saying that electrons at high temperature can come together and synthesize the equivalent of relic neutrinos, then the relic neutrinos that we observe might be relics, but only from other celestial
bodies,
temperature events of electrons colliding together. So what is relic? What does relic actually mean?
Right.
Is it we're only getting light from that far a distance away because our solar system was only born at a certain point of time? So I don't know. But,
right. That's going deep into the theory and the debate of cosmology.
The point is, that's the point, is that if we have protons, electrons, and neutrinos, that's it, right? Now, some people argue that quarks, they're not a real thing.
I could see their argument. It's when the only way we discover them is by smashing particles together. Like, are we really influencing them into existence?
Are you just seeing a vibration on the structure of the physical vacuum?
Yeah.
And interpreting that as a new particle?
Yeah, that's the question. Like, that's kind of exactly. Like, it's very, very, and especially with like LIGO experiments too. It's the same principle. Like, when you have this laser and you're trying to find a vibration that is so absolutely minuscule, like it's like going to absolute zero. You're always going to be influenced by some type of energy radiating from the cosmos.
Well, you're going to be interested in noise. And this is the point of the work since 1988 of Alexander Parkhomov, that's in his book Space, Earth, Human, where he's actually looking at random processes, and the random processes are influenced by something that's common in the cosmos through the Earth, and in all biology. And it would appear, and there's a guy called Simon Schnall, and he's done a study of over 100 papers from 1954 up to nearly the present day, and it's publicly available. You can go and look for it, Simon Schnall, and look at whatever it is, but you'll find it. And they're basically concluding that it is the neutrino flux that does these things. And in fact, Alexander Parkhomov, in his book, he describes, not only can he lens relic neutrinos that are in the wavelength scale of microns to millimeters with a metal parabolic dish, the sort you have for looking at your satellite programs, into a beta isotope like strontium-90, and then look for higher beta emissions to discriminate preferentially. He has this apparatus. He's done 20 years of experiment. Every time we're closer to the sun, the Earth is closer to the sun, the solid angle of neutrinos from the sun doesn't change when we're closer to the sun in any real sense. But what does change is the gravitational lensing of relic neutrinos, or let's say ultra low energy neutrinos that are coming in from the cosmos. So you get an increased flux of those, and you get an increase in the rate of decay of beta isotopes.
That's very, very interesting. So
this is the premise of a book, but also for detecting those things, he looks at MOSFET semiconductor devices. Now, of course, semiconductor devices, you need tunneling, you need a kind of Cooper pairing type event to go on, and so on. What causes these things to occur? Well, he actually uses it to detect neutrino flux. So a random process could actually just be a burst of neutrinos that came from a celestial event. And are we actually looking at a gravity wave, or are we looking at a neutrino flux variation? Now, here's the really interesting thing. 2 years after Frederick Rains established that neutrinos were a real thing, at least you could see it on a phenomenological basis, there was a Japanese scientist, I forget his name, he's a nuclear scientist, and he suggested that neutrinos could explain gravity. Okay?
Yeah. I know who you're talking about.
There's a guy called Bob McGrath, I think he's from CERN Theory Group, and I think in 2010 or 2012, he published a paper that's saying relic neutrinos explain all the observables of gravity. So what I'm saying is that the neutrino flux could be new gravity.
Yeah, it certainly makes logical sense. Now we just need to carry out the experiments to test it, right? That's the point of science, right?
And so when I send these papers to Alexander Parkhomov, well, it's really interesting that people in the West are finally catching up to what they theorized in the 1970s,
right,
already experimentally proven.
Well, I think it's just I noticed that Russia is a lot more open to fringe sciences and in particular plasma ball lightning, and it's really interesting that it seems like we're just now catching up, like as far as mainstream goes.
I don't know whether it's there's different people that know different things.
Oh yeah.
So you mentioned Sapphire. Now there's a guy called Hal Puthoff who might be involved with Tom DeLonge in supposedly releasing things about UFOs.
Right.
However, Hal Puthoff, as I said, not only was involved in that kind of area. He visited a guy in 1992, just after the fall of the Soviet Union in Russia, called Alexander Chernetsky. And Alexander Chernetsky had developed this tube, which had, I believe, high-frequency electrical discharge, and effectively it was a one-sided Sapphire reactor. You had a spherical anode, you had a flat electrode down this end, and you had double layers, which are just a thing. They existed a long time before Sapphire. And in that device, he was able to create massive over unity. He claims that there was some level of propulsion going on, and he also claims that it was emitting waves that were able to change the decay rate of radioactive isotopes.
You just said a very taboo word there too.
What's that?
The over unity word.
Well, I'm just saying what Hal Puthoff observed.
Right.
He saw the device, he met the scientist, and he tried to get him to America, just like he brought Uri Geller to America, and just like he ran the psychic spy program, and just like who else did he brought a guy that I work with quite a lot,
and then
called Dr.
and that's kind of a tricky balance too, because the entertainment value and the entertainment side of things can sometimes mask a lot of the scientific endeavors, it seems like, to make it so it puts people off.
You are so on the money. So what I have here is a few samples. This one here.
Yeah, and that's who was in my mind, but I didn't want to just say his name, but yeah.
This one here.
Hutchison is a wonderful example.
So this is a piece of steel from 1986, and in Hutchison's lab in Canada. It was exposed to a Tesla coil at 15 feet, a discharge as part of the spark gap in the Tesla coil, and he had various interacting radio frequencies in a kind of like reflective aluminium setup, and it would appear synthesized elements in these pits. And you have very specific structures, and you even have a yin-yang here. And I've shared photos of macro and microscopy and SEM photos. This was an aluminium piece of bar. This was from 2007, and we've shared a lot of data about this. I've discussed some data about the study that was done at Synthestech in Russia, in Sochi. They tested this. I'm going to publish that data soon. But essentially, what they found, this was a straight aluminium bar. And it was put on a piece of plastic. You want it on an insulator because these things apparently act a bit like electrons, and they can bleed into other metals, and they can infect other metals. But it started to twist. It started to bend. It wasn't hot. And it went this coral kind of look here with pieces missing from it. And if you actually look, it's quite dense inside. And it actually doesn't sound. I don't know if you can hear this. It's much higher ring. It's not the dead sound of aluminium anymore. And if you actually look into these pits, there are elements in there that were not in the original material, or shouldn't have been. But more interestingly enough, there is nickel, and there is lead. Now, we've already discussed that this system, if it's pushed hard, will always synthesize lead. Why? Because it's the heaviest stable element. Okay, if you go beyond there, you get to bismuth, which is technically unstable, right, with a scary long half-life of many multiples of the length of the supposed birth of the universe. But anyway, lead is the last technically stable element. And so if you've got lighter elements, it will fission between lead and the others, and little pockets of that will push all the way to lead. It may push beyond lead, but if it settles down in the right way, it'll always end up chucking out a load of lead.
Right.
And this is seemingly the way the system works. But the interesting thing, and what I realized from looking at this and other LENR researchers, is P&Tell has found a way around it destroys the reactor problem, because it kicks out protons. Why does it kick out protons? Well, if you look at the exchange reactions on our reaction calculator, very often it's energetically beneficial when you have two nucleons to start with at the beginning and you have two nucleons at the end to kick out a proton. Secondly, if you're trying to synthesize elements that are heavier than calcium-40, you're going to need extra protons to stabilize the nuclei. Sorry, extra neutrons to stabilize the nuclei, which means you have an imbalance of protons. So you have to kick out protons.
Right.
But what's more interesting is that the proton is a fermion. And a fermion can't exist in a very small space with a lot of other fermions. So it's like, you're not welcome around here. Get out. You're kind of upsetting the party. Okay? All of the other bosons can live. And 2/3 or something of the elements are bosons, or the element isotopes. So there's a preferentially nature is telling you it wants to synthesize bosons. Okay? Now, the other thing is it's kicking out fermion. The other thing that's been established in LENR by a guy that worked at Los Alamos National Laboratory and kind of managed like H-bombs and stuff, this guy called Tom Claytor, he established that in corona discharges, a form of low energy nuclear reactions that's done by a guy called Correa Brothers, and other people have done this. They actually use corona discharge to treat water that they feed to seeds to make them grow faster in Germany, which has been studied with a team in Russia as well. That was a presentation at Sochi last year. But anyway, the lead and nickel that's synthesized in here is, in the case of the nickel, there are, sorry, I need to finish the Tom Claytor bit. Tom Claytor established that tritium is synthesized in LENR repeatedly. Okay. Right?
And this is from the corona discharges.
Yeah.
Okay.
And from other systems.
So similar? Is it similar to, like in a vacuum? Is it similar to the Sapphire project?
They're not saying it's tritium, and it could be HD, and it could be 3H. So they're not calling what it is.
Okay.
But if it is tritium, they don't want to discuss that because there's implications.
Then it's not what they want to experiment on. They're going another. They're trying to prove another thing. Yeah. Okay. Sorry.
The point is that tritium has been established in corona or glow discharges, which effectively is one aspect of what Sapphire is doing.
Right.
And as I said, Sapphire is basically a very large double-sided version of the Chinetsky reactor. From, I think it was 1970s. And by the way, just like Tesla, Chinetsky blew up a big power station when he was running his little device. So there's an interesting thing going on there. So the point is that tritium is also a fermion. And so the first and third fermions, the two fermions in the the distribution that you get in element isotopes, those two fermions are kicked out and are left in the LENR ash, But half the time, if you're putting hydrogen in the system, you're never going to observe hydrogen, are you? Because it's like, well, it was there before.
Yeah.
You're going to observe tritium. Now, the point is that if you go and look at P&Tell's patent, he's got around that it's eating the reactor by using these kinetically ejected protons to interact with, with other elements like 7 lithium go to 8 beryllium and decay into 2,4 helium, or with 11 boron and making 12 carbon. So he's getting around that process by using one as like a solid state particle accelerator and the other one as a receiver. So that's what I'm talking about there. Now, what is unique and interesting about what the Synthetech, when they analysed this, and without any understanding that I had, they were just analysing it, cold. They didn't know what to expect. The nickel has a number of isotopes. It has 58, 60, 61, 62, and 64, right?
Right.
Guess which one was anomalous.
Okay. 64?
No. 61.
Yeah.
Why? It's the only fermionic isotope.
Okay.
So it's synthesized it, but it had 3.7 times the ratio.
Oh, I see.
Massively,
Huge,
370%. Huge. And more interestingly, it's in the middle of the isotopes, 58, 60, 61, 62, 64.
Yeah.
Right? So you can't have this kind of like, well, you got some contamination on there and there was some fractionation and you lost the 64 or you lost the 58. No, it's right in the middle of the isotopes.
Right.
Okay?
Balanced. What's the most abundant isotope?
Wait.
Okay.
Lead, 204, 206, 207, 208. Okay?
Okay.
Which was the isotope that was more concentrated?
206?
No, 207. 207 is the fermionic isotope, the only fermionic.
Oh, okay. See, I don't know what the fermionic isotopes of those
and
are.
whilst we're talking about this, the ARV supposedly uses 199 mercury. 199 mercury is one of the only two isotopes of mercury that is a fermion. That's one reason why you would use it, because it doesn't go into the exotic vacuum object. It can build an exotic vacuum object, but it can't. Sorry, the exotic vacuum objects can't live inside the mercury, so it doesn't keep on assemble itself and eat itself preferentially. And by keeping it real and just using that single isotope of mercury, you actually can have energetic outcomes, but the most likely energetic outcome is to produce two other isotopes of mercury. So it's very, very good if you want to create an anti-gravity vehicle to use that specific isotope of mercury. And that's one reason. The other reason is, and I've been saying this since 2017, beginning of 2017, you need conductivity is very important. So aluminium is really incredibly affected because, one, it's got low melting point, i.e. the electron lattice bonds electrically can't hold together very well, and what seems to be the active agent is able to rip them apart and do jelly things like you saw here with it about being off. But the other thing is the conductivity is how much free electrons there are in the material. Aluminium is the fourth most conductive element. But there's also a thing called electron affinity, and that is how much the atom wants to take on board an electron. Well, the most the element on the periodic table that's a conductor that wants to take on electrons more than any other element in the periodic table is gold. And it's a single isotope, 197. Okay? The element, one of the elements that absolutely doesn't want to take on an electron at all is mercury, right? So that means if you have an EVO, an exotic vacuum object, whose ions are made, it's synthesized by mercury ions, okay, it's lost an electron, it's made an ion, it goes into the exotic vacuum object. The exotic vacuum object, according to a person called Shoulders, and I'm building up to something here, a guy called Shoulders, he used mercury preferentially, and he says that an exotic vacuum object can have 10 to the 23 electrons in it, and for every 100,000 electrons it can have an ion in it, and the ion in his case, and in what I'm talking about here, could be mercury. And if mercury is in there, it's frigging heavy nuclei. You've got, for every 100,000 electrons, like 10 to the 5 out of every 10 to the, so you've got 10 to the 23 electrons in one EVO, and then you've got for every 10 to the 5th one is an ion of mercury, and it shields its mass and inertia, which means you can have an unimaginable amount of mass in one EVO. But the whole thing, according to Shoulders, can act like an electron. And if the electron wants to go into something else, like a mercury atom, and replace one of its electrons, well, that's a problem, because the mercury atom says, no, not interested at all. A gold atom would go, come on, bring it on.
Right. So
more than any other conductive element. And it's the third or fourth most conductive element. So it really wants to do that. So gold is key to storing this energy. But mercury is key to, like, putting and doing, like, it's the one that you would want to use for anti-gravity effects. Okay. And so I've said once I've dealt with the mystery of LENR, I want to deal with antigravity, and so I didn't expect the two things to be linked.
Yeah, that's well, I mean, you need a power source first, right? You got to have a power source before you can be able to transverse vast distances.
Yeah. So anyway, so the point being is, it's incredibly difficult to have transmutation going on, right? Because a lot of the physics community will say it's impossible.
Right.
Secondly, you've got multiple transmutations. Thirdly, you've got multiple transmutations that are very common in LENR.
Right.
Fourthly, you've got isotopic anomalies. Fifthly, it's isotopic anomalies that are massive, and they're only for the fermionic isotopes, which we already know LENR likes to spit out protons and it likes to spit out tritons.
Right.
Okay? So 100% certainly that, without a shadow of a doubt, Hutchison was transmuting elements. 100% certain. This one sample tells you all you need to know, and it is only scratching the surface of what these samples can reveal. Scratching the surface.
Right.
Now, he discovered this in 1979. What was he doing? He was working on decommissioning military equipment, and he was getting all kinds of radio transmitters with frequencies you're not allowed to have.
Right.
Okay? So you're not the chances of Joe Bloggs or Joe Sixpack ever discovering this are 0 to much less than 0. Right? Then he was a Tesla enthusiast.
Right.
Okay?
I can relate.
And he would build very large Tesla coils and see what he could do with them.
Right.
Well, one day he's messing around with these things, interacting this with that, and he got hit in the back of the head with a lump of metal. Well, that's not usual. There's no one else in the room, and I don't believe there's any poltergeists there, so he kind of like started questioning things, okay? And so he went on to show that he could effectively teleport material, which Shoulders also did. He wanted...
Philadelphia Project kind of touches on that stuff.
Is that real? I don't know. But what he did was teleport material, it would seem. And it would appear that other researchers that we work with are teleporting small amounts of material from inside their reactor to out of their reactor. And the Russians like Alexander Shishkin have shown that they can take these exotic vacuum objects, they can make them into a neutral version, and they can go through a gas or another medium. And the medium, even if it's a metal, it will take on the nuclei of that medium, and they have characterized that it will leave pits in an X-ray celluloid that are the width and the diameter that are parameterized to a factor of the atom that they took on board when they passed through that material. So there's no doubt that this can teleport material. Okay, so he was teleporting material. He was also making metals go transparent. He was also intersecting materials of different types. Well, you can do that if temperature isn't a thing. If you're dealing at a level which isn't like electrostatic repulsion, and so everyone in the world wanted to get and understand what John was doing. And I can tell you, anyone that got a sample of his material from 1979 onwards will have known 100% certainty, if they were competent and they were able to have an active mind and could look at things critically, they will have known that you could transmute elements in a cold environment without even touching it through non-physical connection. They will have known that. So any of these people that analyze these things would have known that. Now, you only have a phone. You're only able to watch this on a computer because of a guy called Kenneth Radford Shoulders. He invented the mass spectrometer, the same kind of technology, the quadrupole mass spectrometer. This was tested on an octopole mass spectrometer in Russia. But he invented this technology to determine what masses were in elements.
Right.
That was one of the things he invented. But he also is credited as the father of microelectronics because he invented the screening technology to be able to develop and screen and expose to make semiconductors and so forth. So we're only able to look at this because of Kenneth Shoulders. Well, in 1979, some people were looking at these samples, and I believe that some people thought, we need to bring in some serious guns to look at this. And when you're looking at all the people that are available in 1979, the person that would have been top of your list is a guy called Kenneth Shoulders, because he knows about plasma, he knows about atoms, he knows about electrons. He's an absolute genius when it comes to building experiments, you know, and coming down to the nitty-gritty of how things work.
And did he, just to break in real quick, did he have any formal education? Was he like, did he have a doctorate? Anything? No. Yeah, I find that really fascinating. But okay, go on.
And he rejected it.
Hutchison. These
are free thinkers. They haven't become Agent Smiths yet. You know?
Yeah,
so they're able to use. They're able to look with their eyes. And one thing that I learned from reading about Kenneth Shoulders, because I unfortunately only came really across him after he died, was he said, people just don't look for things. You know, if you don't look, you won't even know what you didn't find.
I think it's like Aristotle says, I think it was Aristotle or one of the ancient Stoics said, like, you know, the most common problem most people have is they just don't use their brain. Like, they just don't, you know what I mean? They don't critically think, they just accept. So
they don't believe their lying eyes.
Right.
They look at something, and whatever it is, however surprising it is, to keep their own spatial worldview, they put it into a box that is consistent with what they already know.
Right. It's comfortable. They don't step outside their comfort zone. Yeah.
And the other thing is when they look at something and there's something there, they literally cannot see the wood for the trees. You know, they can't see beyond, oh, that's just contamination. They can't see that the contamination is in a particular form repeatedly across multiple experiments. They can't see it.
Right.
And personally, they're not even probably looking.
Right.
The most of the
it's
problem
dismissed.
They're not looking.
Yeah, it's dismissed.
The Bible says, seek and thou shalt find.
Yeah.
Okay. You know, you have to look to find. You can't find if you don't look.
Right.
It's just not possible.
And the best creature, I guess, to ask is nature.
That I believe that could have been brought to the table to work out what John Hutchison had come across.
That's Ken Shoulders.
Was Ken Shoulders. That was the person at the top of the tree, right? And he started work with as a basis point, looking at the samples, looking at the understanding, and also looking at the work of Winston Bostick. And Winston Bostick, I believe, was tasked in the late 1950s, 1960s or whatever, 1970s, with, I believe, looking at some of the more energetic effects that Tesla was looking into. This is my supposition. I'm pretty sure I'm on the money. But anyway, whatever, he discovered these things which he named condensed plasmoids, and they seem to create the kind of things that are all out there in the cosmos, but just on a micro scale. Okay, just by creating a certain state of matter that was named the condensed plasmoid. And so Ken Shoulders started at that point, and he spent the rest of his life trying to explain this. So one of the brightest people on the planet, and in the end, in an interview or a two-week conversation between him and John Hutchison, which we published in 2010, the only person he really respected in the whole planet was John Hutchison. And he's not even an accredited scientist with all of the labels after his name and
just
all of the published.
But he's a hardcore experimenter and likes to play.
Just someone actually having fun.
Yeah, he likes to play. He likes to play.
It's not even that he was trying to do an experiment. It's like,
right.
What happens if I twiddle this knob?
Right. I think that's the beauty is that, and actually, because he has like that childlike approach to things too, he's able to absorb a lot more than many others and observe things that a lot of people just would dismiss, like you said.
He's unimaginably intuitive and absurdly honest. He's literally pathologically honest. So like when people come to him, like I don't know whether it was he was in Canada or something, and the news crew wanted to come and film something. He says, "Look, I can't do anything unless you come in about 1, 2, 3 weeks or whatever." He says, "Well, we want to come tomorrow," or it was like in 2 days. He says, "Well, I can't have it ready." So we put on a show for them where it wasn't all the way it should be. Now a lot of people in the debunking community like to say, "Well, this isn't real because he did that." Well, John says, "Yes, I faked something. They wanted to see something, so I did it." Like, but I know I've done it.
Interesting.
It's you know what I'm saying? So he's so pathologically honest, even about admitting the fact that he did that. But people use that against him. It's like, come on. people pressured him into doing something he didn't want to do. He told them the honest truth. It couldn't be ready in this time.
Right.
So everything he's ever said to me, and that's been a lot, has been true. You know. So the guy is pathologically honest. Now, you mentioned, and this is where I'm coming to, believe it or not, you mentioned that people get confused between science fiction and that something is possible because it's actually real.
Right.
Right? Is that deliberate? I'll tell you what. In 1997, Kenny Shoulders and John Hutchison, they spent 1 month with like Larry King, the producers of blah blah blah, and the producers of Star Trek. 1 month to discuss what they should put in their science fiction shows that were going to be possible in the future using aspects of this technology.
Yeah.
It isn't that there is confusion. It's as I would call it, inoculation. It's coming down the pipe, my friends. It's coming down the pipe. And by the way, we probably already used it before as a species, but there's a whole completely different.
That's a deep rabbit hole.
That's a really deep.
Yeah. Yeah. So there was one question that came up, and it has to do with Amaza gas. Let's see. Slobodan. Sorry if I slaughtered your name, but he asked if you will be trying to use tungsten boride with a massa gas, you know, because his thought process is tungsten and boride would equate to gold.
So yes, and you can do that on our calculator and find out that that's the case.
Right.
So yes, you're right. I mean, it's not like I haven't been blatantly obvious about where you can go with these things. If you can take elements and you can make them into other elements, and that our online calculator correctly predicts all of the elements that were used by the alchemists, and it took me 50 seconds last year to demonstrate that the alchemists were using exactly the right elements that were available to them at the time. I also suggested that you can use the same calculator to choose elements that would preferentially have an outcome.
Right.
And the other thing is that the boron is highly active, and I've specifically said why this is, and it's the same reason I chose indium. Boron, like lithium, like indium, like gadolinium, and like cadmium, all stop neutrons. What is a neutron? A neutron is a proton and electron bound together by a neutrino, because a neutrino comes out of it when it decays. What is actually a neutron? Is it just what is stopping the neutron? Is it the fact that it has a relationship with a neutrino? Is it actually stopping neutrinos? Well, we know because Alexander Shishkin from Dubna Science City, he has actually got a string vortex soliton, a condensed neutrino detector. And this is made using a standard boron 10, which is the isotope that has the high Barnes stoppage power of neutrons. He lowers the voltage from 1,000 volts to 570 volts, and he gets a signal that's something like 52 times bigger than a neutron when his string vortex soliton generator hits it. So effectively, the neutrinos are coming in, and they're causing this interaction with boron. Boron, in my view, is an excellent material to mix with almost anything. And in fact, in the other room, from about 2 and a bit years ago, I have some boron trioxide that I meant to run in the NOVA reactor for precisely this reason. And so, you know, so I took a couple of elements to test with the Amaza gas. One was indium. The reason is that we already know that neutrinos, from Alexander Parkhomov's work, he's proved that neutrinos can accelerate the decay of beta isotopes. Now, the 87% or something of that order of indium 115, which is the neutron stopping isotope of indium, is 87%. It is a beta emitter, and that's a number of aspects. So these are the reasons that I took that. One, it's an extremely low melting point. Everyone testing HHO gases and you know, Brown's gas type things and oxyhydrogen gas, they were always trying to choose titanium and tungsten and fire brick, and because they were high temperature, so that it's spectacular that it can melt it. I wanted to go to the other end of the table and find something that wasn't going to burn in air readily, and that was an extremely low melting point, 152 or whatever it is degrees, 150 something degrees centigrade for indium. But more importantly, was a beta emitter, had a large proportion of beta isotope emission, and that it was a very long half-life. It's 30,000 times the life of the universe half-life. That's why it's still 87% if we accept that there was a birth of the universe and not just the birth of the solar system, right? Or birth of the near universe.
Right.
It's 87% is a beta isotope. What does that do? If an EVO goes in, it causes the rapid decay from 30,000 times the length of the universe to a near instantaneous decay. It emits an electron. What does an electron do? Take the string vortex soliton, which is a electron depleted exotic vacuum object, and it chucks electrons at it, which makes it into a non-electron depleted exotic vacuum object, which can then massively transmute the elements because it's then fired up. It can suck in all that.
Right. It's a black hole.
Indium.
It's redispersing.
Well, it's a black donut.
Black donut. Well, I mean, technically, a black hole. What are we looking at when we're looking at a black hole, right?
Well, you're looking at nothing in the center, and you're looking at a fiery ring around the outside.
Right. So
it sounds like a black donut to me.
Yeah, it's black donut, right?
Well, no, there's a white donut and a black donut, and you can call them a white hole or a black hole.
Right.
Okay?
Right.
So, well, actually, not a black hole. You call it a black plasmoid, and
the other one
plasmoids.
Is
but it's not really a plasmoid because it's not really got the electrons in there. Anyway, Shoulders calls them black and white EVOs, and so. If you saw a donut and it was glowing, then you could call that a white EVO, and one that you can't see and it's still it's like
doing something,
black hole,
right?
And it's sucking in material,
right?
That would be a black EVO, right?
Right.
It's just on a bigger scale, okay? So in the case of the black EVO, it's this neutrino condensate that Shishkin, but not only Shishkin, Bogdanovich's team at the Moscow Physics Laboratories. You have the people that discovered most of the heavy elements on Earth in the last 15 years or whatever, at Dubna Science City, and then built the Soviet nuclear weapons. They have established what it is, and also the Moscow Physics Laboratory have independently observed the same phenomena. What the Moscow Physics Laboratory did in work in 2007, they had an electric discharge through a water jet. Right. Electrical discharges through it, very very similar to Suhas-Ralkar's foil generation system, and they found these donuts coming off. Sometimes they were white, but sometimes they were jet black, and behind them you had a plasma discharge, but the light is not able to get through the black donut, which means it's stopping light.
Right, it's absorbing it at least. Like
it's a black donut.
Yeah.
It's eating those photons for breakfast.
I would love to see some experimental video and yeah.
Well, you go and see the pictures. It's public. Go to the MEHPL website and look up Bogdanovich, or just look for Bogdanovich on our YouTube channel. You will see those links. But more recently, in May this year, he published work where they were continuing this work from the early 2000s. And they've created these things where they've observed these plasmoids moving around on the surface 2 days after the experiment, and they're moving around, maybe transmuting the elements, but producing light, right? And they move at 2 microns per minute or something, and they've got videos of these things moving around. And not only that, they cluster into these regular arrays, which are quite similar to those arrays that were published in, I think, 1993 by Matsumoto. The impact of them on his things that we have actually observed potentially similar things on these Amasa vibrator plates. So, all of these things are tying in together, and you have a situation where, okay,
it almost doesn't even matter what the medium is either. It seems like the medium almost is not what's we're fixated on the medium. I don't go. Proceed. I don't want to digress here. Go ahead.
Well, is there any other questions? So essentially. Blah blah blah.
He was asking about Mazda gas. As a maser. So actually, before we got on call too, we got into a conversation, it's probably the simplest term I think I've ever heard anybody, the simplest way something's put, and that's often like the best way to describe something, of kind of your hypothesis of what's going on, and it had to do with like lensing, and you told a story about that. Could you go over that again? You remember that story?
Well, firstly, if you go to, I think even today it might be, or a couple of days ago on Zero Hedge, there's an article where they've created a incredibly powerful laser using a plasma mirror. And that I'd actually talked about this in this YouTube stream previously,
right?
But it's worth, because Slobodan is online right now. It's useful to go over it again, and essentially a plasma mirror is able to produce a laser intensity and focus that's so intense, they're saying, that they can rip through the fabric of space-time. And so this is like hot off the press. But Slobodan, this is what I propose is happening, certainly when we were cutting through, and I said it looks like a laser, and then when you told me, Slobodan, that you had observed mostly OH groups, you need to go and look at the work of Mondiani. I think he's an Italian guy from the 2010 or 2011, 2012. He's doing electrolysis experiments and plasma onto water experiments, and he finds that his electrolyte gets extremely soapy, i.e. it's alkaline, i.e. it's synthesizing more OH groups. He suggests that's because it is producing deuterons from electrons and 2H. And that may actually be the case. So there's a lack of protons left to resynthesize pure water. So you end up with an excess of OH groups, which might be what's happening. But the interesting thing about OH is, as I said to you previously at the conference, Slobodan, that it's one of the most abundant interstellar gases, and that it self-mazes. Now, when I looked at that coin that was exposed to the Amarza gas, and it looked like it did a laser cut through it, if you had a copper which is very reflective to light, and you had the plasma mirror at the other end, the gas is coming out, and at some point there is no ignited gas. So the end of the gas plasma ends just before the nozzle of the Amarza gas jet. So you could have a maser, and OH self-mazes. You have an end which is a plasma mirror, and you have a copper thing.
So standing waves. You're creating standing waves of energy.
Yes, and it ends up unimaginable energy concentration. And if you've also got some nuclear reactions going on because of the 0.2% identified atomic hydrogen that's also supposedly in the Amarza gas, you've got that energy coming out in high energy photons. You might have a situation where you have an unimaginable energy concentration, and just like it did on the video, it ate a chunk through that coin.
At what temperature too? Like that's the even more surprising, like, because
it wasn't at the melting point of copper.
And from at least from the thermal imagery, right? I mean, you had, what was the top temperature that you guys measured? It was.
I think the top temperature we measured in the whole day was when we mixed when there was with the one test that we did with 10% propane and 90% Amarza gas, and we put that onto the titanium 1 millimeter sheet, and it registered something like 903 degrees or something.
But melted the titanium.
No, it didn't melt the titanium.
Okay. Just heated it.
In the case of the melting titanium, we only achieved on the backside of the plate, I think 700 and something degrees C, but titanium melts at 1,700 and something degrees C. It's not melting it. And we all wrote
right. It's not technically melting
when we saw carbon on the PTFE, these are experiments you can go and look at the YouTube video on our channel. But when we saw the carbon forming on the PTFE, and it not melting like as quick as it melted through polytetrafluoroethylene that's supposed to go and melt or degrade it to 300 degrees C, and it wasn't doing it as fast as titanium was. That opens some questions, and we saw carbon forming on it. Now that might be carbon stripping because it's CF, and it's CF2. It's like a polymer of carbon and fluorine, and it might be removing the fluorine in some way and taking the making hydrogen fluoride or whatever and stripping the carbon out. He came up with this, in trying to explain it, he admitted to something that was a test that was done at a Japanese university, where in 2003 that it was forming nanocarbon all over the titanium, but also it was synthesizing aluminium. And this is really, really interesting, because how are you getting aluminium from titanium? Well, if you do the reaction between those, you can have an exchange reaction between 14 nitrogen, which is a boson, so it can easily go in and live in this structure, and 14 nitrogen, which is a boson, and that can live in this structure. 14 nitrogen is 78% of the air you breathe. This is being done in air.
Right.
So you can have a situation where you're on an iron sample, and you've got these exotic vacuum objects, and they are fusing the nitrogen in the air, and it goes to, I think it goes to hydrogen 1H and 27 Al. Okay, so and both of those are proton boson fermions, so they want to come out. Right. Bear with me on my logic.
Right.
You've got two bosons easily want to go in. They're 78% of air, right? Iron doesn't want to change. You've got the EVOs coming to the surface of the iron, right? Doesn't want to change. It meets the air. The air is then being fused into preferentially 1H and 27 aluminium. Then you have, that is unbelievably energetic in the many mega electron volts.
Right.
That causes surface oxidation with the other sort of 20% or whatever it is in the air of oxygen. You get iron oxide. Then you have extremely hot iron oxide right next to extremely hot nuclear, fresh synthesized monoatomic atoms of aluminium. Right. These two would fuse together and they would look like thermite.
Yeah, so I was about to say, it sounds like thermite to me. That's exactly.
And you know what you would end up with? You would end up with hematite spheres and some traces of aluminium oxide. It would look like thermite being used, but it would be this technology. I don't even want to go where I'm going there.
Yeah, we don't have to go. We don't have to go down that rabbit hole either. I don't want to. Yeah, we won't go that way.
So there's your answer.
But if you could condense it into an iron form, right? The theory or the hypothesis you have, to simplify it to just.
I'd simplify it like this. It's essentially you're creating an active agent. Let's call it a black donut or a white donut. It doesn't matter. But even just call it. It's an actor. It's an actor. Okay. You have an actor that is able to take material and is able to mash up the nucleons and spit them out. Firstly, it does it all within it. So the energy within it creates thermal energy. The thermal energy can be expelled as synthesized neutrinos.
So a microgalactic nuclei in a sense.
Well, just imagine you've got your Dunkin' Donuts donut, but the donut is actually made of electrons, and the electrons attract ions. In fact, they even ionize to a certain degree,
right.
in a way, because they have their own kind of like double layers, let's say.
Right.
But let's not go there. Just say that they are able to take ions of material inside them. And when they've got the ions of material inside them, they are then trying to pinch that into an extremely small, it's not a black hole, it's a black ring. Okay. To an observer a long way away, it would look like a black hole because shit was going into it.
Right.
But up close and personal, and when you look at it on other things, it's like a ring. And inside that ring, the things that can occupy the smallest amount of space-time are things that are happy playing alongside each other. And essentially, it's all energy waves. And
right.
It's only outside of the device that things become electrostatically physical to us. But inside, they're not electrostatically physical. The electrons have gone, and their wave functions are all entangled, as long as they are bosons and they're willing to play nicely with each other. But inside there, as more material comes in, it can synthesize fermions. Okay, but they get kicked out.
Do you think it's redistributed in another, like the black hole white hole paradox type of situation? At times, I mean, or do you think?
Well, what is a black hole white hole?
Right.
You get a black donut, which is the same thing, but with not in the white hole state.
Right.
In the white donut state.
So it depends on if it's absorbing its surrounding materials or not.
You would see material going in, right?
Right.
A white hole, you could say, is a white donut, but the white donut is expelling energy because it's sucking material in, but also expelling it.
So that's why it's so fascinating to me for teleportation purposes and stuff like that. It's really interesting to think about, talking about faster than light travel. Like what's going on with space-time and stuff, like space-time trying to alter space-time, and the Kubla drive or whatever it's called. that's the very principle that they're trying to do, is like to create that.
Whichever path you travel down these various threads, you always end up at Hal Puthoff.
It's interesting. Yeah, that's I don't know if that's a good thing or a bad thing. It's kind of it's the entertainment. He's the spokesperson, I guess. He's someone who is very open to just say.
No. I worked with George Eagley in 1983. Hal Puthoff sent a guy called, I think, Bernie Heisch or something like that to meet him because he was investigating metal bending teenagers in Israel. And of course, Hal was interested in that time, so sent him. And then Dr. Eagley becomes the first Soviet-era scientist to go to, I think, Brookhaven National Laboratory, the first Soviet-era scientist to go into a U.S. nuclear facility. And whilst he's staying in whatever accommodation he had, there were some books in the attic, and one of the books was talking about plasma balls, and he got really interested in ball lightning. And then he'd been doing like 20 years or something of studies of anecdotes of ball lightning, and this became a military report. It was a major part of a military report which has been declassified about, that they wanted to find out. I think it was commissioned in October 2001, and they reported back because they wanted to know anyone in the world that had been doing any research on anything like ball lightning. And of course, he had done this huge body of research, and this was the guy that came with me to test the Amasa gas system. Right. So, but the same guy, I think it was Bernie Heisch, actually went to Canada in the early 80s on the instruction, as far as I understand it, of Hal Puthoff, to visit John Hutchison.
That's interesting.
And in the presentation that Kenny Shoulders in 2006 gave to MIT, where one of his pictures is this guy, I think Bernie Heisch is his name, he's still alive today, he still works with Hal as far as I understand it. He's actually holding one of the classic pieces of John Hutchison's metal up with it broken in the middle. It's all interlocked.
Very serendipitous.
Is it?
Well, no, probably not. There's probably a very good reason for all that. So.
I mean, interesting people attract interesting people. When you're running out of really interesting people, the very interesting people like to meet the very interesting people. And quite frankly, Kenneth Shoulders said in 2010 he has no idea who on earth he can speak to, because most of the things that's going on in his head are so far ahead of what anyone else is even capable of comprehending.
To find like-minded people that can actually, absorb kind of what...
And it's a real shame, because I think in 2010, Kenneth Shoulders wanted to start distributing papers where people could work, like a kit description for $5, and then he wanted a kit for $40, and then he wanted. So he already was trying to do what the MFMP was kind of set up to do. He was already proposing that, but the internet wasn't really at that level of where people were kind of engaging these topics like they are now, like you're enabling now.
Right.
And so it's. So how are we doing with it? Have we got any questions?
No.
Drive, yeah.
No, well, we're 2 hours and 30 minutes in. This has been quite an experience. It's been a lot of information. Like, now my mind's like, I'm just reeling. I'm like, man, there's like so many ideas are running through my head. So,
I tell you, can I say this?
Yeah, absolutely.
In the 2019 Rugby World Cup, this is an energy drink. and this is an energy drink where the water is being synthesized with Amasa vibrator plates.
What is that? What is that drink?
It's an energy drink they're going to sell as an official product for the 2019 Rugby World Cup.
Okay, so that's what he produced.
He produces all kinds of things. The crazy thing is that Adamenko learned the Russian method of cold nuclear transmutation from 1957. That's where he started. Okay? Right. The Japanese, like you had all the things that people are talking about now, Matsumoto did in the early 1990s. Roishi Amasa has been selling face and beauty products and drinking water and systems for purifying water and for growing fish farms and for deactivating radioactive nuclear waste.
He's got to work with the system at play.
For 16, 17 years.
Yeah.
And in the West, Oh my God, we're still debating if it's real. I mean, wake up,
interesting.
for God's sake. People have this meme out there. Oh, I'm very woke. Oh my God, really? Really? Are you woke?
Yeah, well, it takes time for people to accept.
This is technology that humans, in my opinion, were designed to live around.
Yeah, it's if speaking as far as Star Trek terms, like, okay, so we have our cell phones, we have our tricorders, we have AR and VR coming, so we have the holodecks. Now it's a matter of how do we get our energy, which is a crystal, interesting enough, right? And that's what metal structure is, and then into the whole new level transmutation is, you know, a replicator, right? And so to be able to do 3D printing with energetic means like this would be...
No.
You know what I mean?
Forget it. Listen to what Kenneth Shoulders said.
Okay.
Listen to what Kenneth Shoulders said.
All right.
With one of these structures, you can put into it a frigging mouse, right? And then you split the structure and you re-energize the structure up to the same level, and you break the structure, and out of it comes a mouse, and you break this and out of it comes another mouse, and they're exactly the same.
Replicator.
In fact, they're the same thing. They're just in two locations in space-time.
Replicator, teleportation, all these things were science fiction, but if we can imagine it, then how can we? It's more opportunity to create it, right?
He's saying teleportation. You would act like, you know, he's implying in that the suggestion is you're not necessary. You can shift from point A to point B, but you can be in point A and point B at the same time, and you just kill the other one. You copy and paste.
Yeah, that's yeah. So interesting.
If you don't turn up at your destination, then they don't delete the original.
Right. You can go. You can recover it.
You can
keep
trying.
Recover the universal data.
CPIP. If the you know the verify bit doesn't come back to say you've arrived.
Well, that's what's so exciting.
It doesn't delete the original.
Exactly, and that's what's so exciting about a lot of this technology that is on the fringe, is you're able to explore those ideas and those possibilities.
My friend, how is on the fringe when you've been selling?
Right. Because, well, how is he going to make his?
Element.
But how is he going to make his income, right? How is he going to be able to operate in the system? He has to do those things, right? He has to sell that stuff. Otherwise, you know, how is he going to make his money? That's
the point is that he is transmuting elements. That already is scary to all of modern science, right? Even though 14 nitrogen, 14 carbon and calcium, potassium 40 is transmuting in your body every day, it's still scary to a lot of scientists that the idea that you can transmute elements.
Right.
He is changing radioactive decay rate times. He's not the first. You've got go and look at the introduction video for Space Earth Human, Alexander Parkham's book. I list through a selection. It's not exhaustive by all means, but it's a selection of the people that have observed this phenomena of cold fusion systems changing radioactive isotope decay. Right. The real problem for this technology is it's not just about making excess heat. It changes everything. Yeah.
It's about actually getting a depiction of how to manipulate matter just using energetic checks and like balancing. It's a balancing act.
If you thought you had a problem with the energy industry, what would you have a problem? How much of a problem when you had how much of a problem would you have when you had the problem with the energy industry, the communications industry, the transport industry, the medical industry?
It would be it would be a extremely disruptive technology for sure, and I think that's a huge resistance to it. I don't know of too many other disruptive technologies than one that will influence energy in general and how we look at energy. You know.
Shoulders again in 2010 said this. He said, "If there's something you wanted to do and you wanted to do it really well, this would probably be the technology that would do it best." Something I'm paraphrasing here, but it's very close to what I've just said. You can go and read the transcript. Basically, there's almost nothing that you would want to do well. He says, I don't care about anti-gravity, just give me propulsion. Propulsion's much more useful because I can use that in space. Yeah. I don't need something to push against.
Right. Propulsion.
I don't need gravity to go anti-gravity against.
And all propulsion is getting from point A to point B too. You don't have to look at it.
It's very simple. Yeah. It's very simple. You get a lump of ions, You chuck them into an EVO, they lose their mass and inertia, you accelerate it from point A to point B, and at this point you destroy the EVO, and the atoms have gained that speed. Let's say in a normal cathode ray tube, you could accelerate it up to the speed of 1/10 of the speed of light. When it hits this other thing, it pushes it. And you've literally broken fundamental laws of physics. And as Ken would say, man-made laws.
Right.
Wrong.
That's
all wrong.
Well, on that note, I really appreciate you coming on. It was a fantastic experience. And down the road, we should do it again for sure. And then, yeah, I mean, is there anything you're working on that you want to tell people about, or anything like that? Anything you want to check out?
Right now, so I talked through my choices for indium. It was soft, malleable, low melting point temperature. 87% of it was a beta isotope. We know beta isotopes can change very, very fast. This one has a 30,000 times the life of the universe length. So if we can change it quickly, that would be great. It
what about bismuth?
Electrons can feed an EVO. So then what happened actually was we wanted to test the before and after material in Alan Goldwater's Magic Sound Lab in California. We had the material that came out of the Amasa vibration system, which I said, don't bother looking at the before material in case we've got nothing on the material that started, that we've treated rather. But there was massive apparent transmutation, and in particular structures, which, as I say, it's not only transmutation, it's about morphological and spatial, where those transmutations are occurring. So with that vibration, with that system, we said, yes, it looks like it's done it. So let's look at the starting material. So we had already previously cut off some segments of the material that we took to Japan for later testing. And we put that under, and it just had a bit of nitride, a bit of oxides on the surface, as indium does when it's exposed to air for a period of time.
Right.
So he said, well, let's see if we can clean it to cut off any dirt or whatever is on the top layer. And he put it in this $40 bought off a very popular site for buying things off, site, ultrasonic denture cleaner, for cleaning dentures.
Ultrasonic, baths, I've used one.
Nominally claimed to be at 42 kilohertz with about, I don't know, some ridiculously low 25 or 35 watts input power.
Right.
He's done the sound analysis on it. It looks like it's actually around about 46 kilohertz, but that's on the threshold of his microphone because it's a 96 kilohertz mic and blah, blah, blah.
Right.
Anyway, so he's established that it's around the ballpark of the claimed oscillation frequency. He put it in there. Now I'm looking at I've already looked at the one material. I looked at the before material without cleaning. He went away and cleaned it. He came back, exposed it for just ionized water and a bit of -90 cleaning fluid. This has certain elements in it which we know. He then gave it to me. I put it on the SEM table, put it in there. He went off to get a coffee. And I just put it on the SEM, and it was just literally mind-blowing. There were 3 massive 2-millimeter diameter blast craters. The rest of the surface was nice and clean. But in these blast craters, there were blended into silicon dioxide from the indium, blended into fluorine. And when you run the calculations on the calculator, these kind of things make sense.
And this is inspected on the SEM before and after, right? The actual sample.
So it would appear that there was massive transmutation occurring. So right now, we bought some more indium. He's putting it under with the 2.5-inch sodium iodide detector, arranging that, and on Monday, that is tomorrow,
excellent,
Californian.
So
we'll start to run experiments.
So if people want to see your data and all the experiments you have one place to go. What would be the one spot to go? I can link it in the description.
So to look at our historical work, we have a site called quantumheat.org, and there's a donate page on there if you want to find out how you can support our project. It is basically entirely funded by people who are willing to give their own time and resources, people in the community that are willing to analyze our work and offer ways forward, and the generosity of the crowd. this means that we can maintain our independence. We can go and visit John Hutchison. We can go and visit Royce and Amaza and not be a threat to them. So we can tell them stuff. We're not under any NDA for doing anything. They can tell us stuff, and we can merge minds and find an answer to this problem. So any help, massively appreciated. And everything that you've heard about today and everything on that site was only enabled by the combination of these factors. So that's one thing. Now, principally right now, because it's not very responsive, that side, it was parked as a historical document, and we work through Steemit. We have a steemit.com /@MFMP, and we also have Facebook, Martin Flieschmann Memorial Project. It's a bit mouthy, but we wanted the full name of the project in there. And we also have a Twitter feed. And from those, you'll be able to find the most common things that we're doing and updates on our work. And then our YouTube channel, again, Martin Flieschmann Memorial Project. There is a huge body of work there. You can see some of the most recent stuff, and there will be a lot of really, really interesting stuff. The stuff that from the analysis of this done at Alan's, I said to Alan when I analysed this, I said, Alan, we cannot even begin to comprehend the significance of this data. It's literally going to melt people's minds. And this is just one small sample from John Hutchison. It's absolutely breathtaking what's gone on in this sample. A small amount of the analysis so far has been shared of this, but really, and from this sample and the data that is already in the pipeline to go out, you should be able to work out the frequencies that would be required to do this in a non-physical way. And we are literally then going to be living in a whole different universe.
Well, that's pretty amazing. I'm excited about it, and I have my own stuff I would like to do, and it's always a pleasure to learn from you, and as well as so many of the people you spoke about. And like I said, I'm so grateful for you coming on. I appreciate it so much.
It's a pleasure. It's a pleasure. Sometimes it's faster just to talk these things. So people often say, "Oh, you're like a fire hose," and it's like,
yeah,
"Oh God."
You do unload some serious amount of information for sure, but a lot of times it's bite sized, and you can get little bits and pieces. I'll have to go back and look at it, and maybe I'll cut up some of this and for promotional use of quantum heat and stuff like that. So
that'd be great.
Help you out. So cool. Well, I appreciate it so much. And
thank you, Dan. It's been a real pleasure, and it would be nice if people could ask. Is there any questions still out there?
There'll probably be later on comments, and I'll come back to you, and then I'll hit up my social media feeds, and we'll try to.
I just want one closing. That there wasn't particularly some specific things. There were some specific things, but to summarize, you can start by taking 2 pieces of carbon, 3 12-volt batteries, and sparking them together. That's one way. You can start by getting yourself a $40 ultrasonic denture cleaner, and you can get about $50 worth of indium foil. And if you follow our experiments over the next couple of weeks, then you may see that transmutation is possible. We need to verify that, but it does look like it's pretty strong, and it's following the science. This
right.
came about through reasoned logic. Then the last one is, if you have an HHO generator and you know someone that does, you can do what Slobodan Stankovic did, and he took some carbon and he blew his torch on there, and there was apparently massive transmutations, the same kind of transmutations that George Ohsawa saw in the 1970s and 80s that has been replicated. I would recommend, as I recommend to Slobodan, that rather than scraping off the sample, you actually look at it in situ, so you can see the morphological and the spatial arrangement of the material. We did this with tungsten, and you will see in the next couple of days, or the next couple of weeks, that what happened with the tungsten that was exposed to a Mars gas and with the indium that was exposed to Mars gas is something happened just under the surface, and it caused transmutation, and it blew off the top or caused a massive ridge. And so these are I've given you 3 different examples. One is at a price point of almost nothing. The next one is kind of like dinner money for a primary school level, but the third one is within a lot of people's means to do. And between myself, the work of Royce and Amaza, the work of Dr. George Eagley, and the work of Slobodan Stankovic, and referring back to the Yule-Brown work in 1991 with radiation remediation, we're starting to open the lid on this science. And so thank you very, very much. And thank you to all the listeners, and both right now in the live stream, but in the future, for sitting through this. And I hope you get something that can move this society and this planet forward.
Beautifully said, my friend. Well, until next time, guys, thank you for watching, and thank you to my guest. And yeah, have a wonderful day and enjoy every present moment to the fullest of your ability.